Hello, everyone. Welcome to day 3 of our first annual SU2 conference. I want to thank again the speakers the past couple days. I think we've had a great 2 days full of talks. And for those of you who maybe had a little bit of trouble yesterday with audio or maybe missed some portions, just a reminder that we are putting very high quality videos up of the 2 days. So you'll find them on the conference page linked there, including the one from yesterday with the correct audio at the beginning. So please go check that out if you want to see the final product, and all the content and slides are posted there as well. So for today, what we're going to do is start out with something a little bit different. We're going to have a session here at the beginning for the first 45 minutes where we talk about kind of ongoing developments and look ahead into the future. And we're hoping that we can really make this interactive. So we have a few slides to kind of lead the discussion, to seed some ideas, and then sort of in the latter half, we're going to try to open it up, get a lot of feedback from you all out there, potentially take some questions, get some people turned on as panelists so we can sort of answer things and have some discussion and just do our best to get as much feedback as possible. So what I'm showing here is a slide set, just as I said, to get the conversation started. One thing that's been really great in the past at the developers meetings is, over the past few years, is to really sit down together as a team and just talk about what folks are working on in the code, and also what things are missing and what things are ranked sort of at the highest priority level, if you want to call it that. What features and issues are people having that we should promote and really put emphasis on as a team. And so we want to do something very similar here with the entire group virtually, and we'll do our best to do that. So why don't I get started? So what are the objectives of this session, apart from what I just said? We want to review the past years. So as I said, we've had these 4 meetings now. We've, over those years, we've written down a bunch of priorities as a team, and we've since worked on them. So the idea is to look at what we said and look at how we've been doing in accomplishing progress toward those goals. Then we'll talk a little bit about what areas we know people are already working on in the code for the coming year. But then the real key of the talk will be to, looks like they're frozen. Juan, can you hit next, please? Is a prioritization of efforts and getting additional ideas from you all, as I said. So we're going to do this in a couple ways. One is through online polls, which we'll have in the second half. So we'll actually invite you guys all to look at some options and vote, your priority list, what you're most interested in. And then a second way we want to do that is by having you just write things directly into the GoToWebinar question box. So feel free, while we're talking, we'll be checking the GoToWebinar question window, and we'll be taking your feedback and maybe reading it out loud, or even if you would like to make a comment, you can let us know there, and we can turn you on so you can unmute you and you can share your comments. Next. And of course, a big part of this is to enlist your help, everyone out there, the team, but also the folks who are here as users and members of the communities as points of contact, getting help with development, testing, etc. I mean, the project works best. It's the most rich when we have participation from as many people as possible. So the way to think about this talk in the end is, imagine we're having this meeting next year. We're going to have a very similar discussion, and what topics will we want to talk about next year? What kind of things will you be showing next year in your slides? So that just puts you in the right mindset for the kind of stuff we want to talk about today. So next. So how has this worked in the past? Well, in 2017, when we met at Stanford, we did a very similar exercise. And so we had at that meeting a discussion of our development priorities. And so again, we were sitting around the table as a team. Everybody kind of had their hand raised, was asking a lot of questions, was proposing new topics. And we had the idea that, okay, we should do this every year. We should look at these topics. We should look at them each year and check how we've done. So first, I'll put up what we said we would work on in 2017 as a list. There's kind of a lot of words here. It's a bit of a long one. I'll let you take a look for a second while that's up before commenting. So you can see that the wish list, if you want to call it that, spans everything from new physical models, performance improvements, to more usability type features like GUIs and documentation, things for optimization and design. So it's quite a long list, but you'll see that over the years, if you go ahead and hit next, we have actually accomplished quite a few of these. So what we're going to show is the kind of checks, pluses and X's here of what we have accomplished. And let's say this is significant work completed. Obviously, this is a bit subjective, so it's hard to say that things are, not everything can be complete. It's so black and white. But all the green checks are things that the community and the folks involved in the project have put a lot of time and effort into and have seen a whole lot of development on over the past few years. Now, the red X's are places where we could do better, or things we just haven't had the bandwidth to get to yet. And so some of the things that we haven't gotten to from this year, GUIs, some of the scripting, surrogate models, geometric constraints for design, et cetera. But you see, by and large, since 2017, we've made a lot of progress as a team on a bunch of these topics, pretty wide ranging. So we can be proud of that. Let's go to the next. Now, we did the same exercise in 2018, and this list now is unordered. And so what I'm showing is a little snapshot on the right of, whoops, go back. There we go. What I'm showing is a little snapshot on the right of our handwritten lists of priorities from that meeting. So we did the same exercise where we all sat around the table in the room and had somebody writing on these large sheets of paper what our wish list was. And so I've transcribed, you can't probably read it off that picture, but I've transcribed what's there on the left. And so the same exercise was done, and you'll see pretty good coverage again of things that we've accomplished. So the same idea, green checks are what we've worked on quite a bit and made significant progress on. Red are things we need to keep working on, but a lot of interesting things that we did pursue over the past couple of years. So things like cleaning up the config object, multi-point optimization, putting in wall functions and wall models, multi-physics, a lot of things on robustness and convergence, which I'll say a little more about in a minute. Verification by manufactured solutions, for instance. So, we do take these lists seriously, we write them down, and it really does help focus our effort. And that was the 2018 version. So let's go to the next. Let's talk about 2019 quickly. So last year we did things a little bit differently. What we had was a set of breakout sessions where we tried to divide up the folks that were in attendance into some groups so they could talk about separate areas in smaller groups a little more effectively. And so we broke out into groups. One team was looking at MDAO, another was looking at flow physics, and another was looking at robustness, performance, scalability, and V&V. Sort of a long acronym, but we broke into these groups and sat down and talked about what things we wanted to work on in the code in those areas and how we were going to divide that work and tackle it. So next. Now, as an example of that work in this robustness, performance, scalability, V&V group, I'll give you a snapshot of a slide that we put together after the conversation, which was our envision code requirements, right? So what things do we want to work on for this particular area in the code? And so what you're seeing on this list here are things that are related to performance and scalability. So things like improving multi-grid, new limiters, robust convergence, linear solvers, fixing large CGNS type meshes, et cetera. And you're probably noticing now, you've seen 2 or 3 years of these development priorities. You're noticing some what I'll call repeat offenders. So things that we're not quite getting to. And I'll comment on that in a little bit, or we'll comment on that in a little bit. But again, if you hit next, you'll see that even on last year's set of priorities from this one team, and the other teams had their own lists, we've accomplished quite a lot. So I'm very pleased to say that over the last year, we've put in a lot of work on robust convergence, both in terms of realizability checks, improvements to Jacobians, improvements to the way CFLs are adapted to ensure good nonlinear convergence, things like this. We also have, from what you've seen in the meeting, hybrid OpenMP MPI and optimization of data structures for performance optimization purposes. And so we're really making good progress on these things, but like previous years, a few are slipping through the cracks, and we haven't gotten to them yet. So with that, I want to bring in Juan, who's also here on the line. He's going to jump in and take the next few slides to talk about progress and also polls. So go ahead, Juan. Okay, I'll go ahead and take it. So I think we're having a little technical glitch, so I'll keep going from here. So let's just summarize what I told you, because I know I gave you a lot of information all at once. So let's talk a little bit about the successes from the previous years. So here are things that we made major progress in. So robustness and convergence. You can go ahead and just animate the whole list, Juan. Interfaces to external packages, performance improvements. So things I just mentioned, like hybridization, data structures, Jacobians, etc. We've improved the code organization. So this is a very important one. Things like just cleaning up white space, separating files into smaller chunks. We saw in the welcome talk that we've been sort of making each of those files smaller, more easy to handle and develop, and fewer conflicts. A lot of work in different physical models. So you've seen the work by, for instance, the NEMO team, working on non-equilibrium flows. Multi-physics problems like CHT and FSI are really starting to show a lot of interesting results, including their adjoint methods, which you've seen in this talk. We've successfully fixed up some issues with large mesh support. So I'm pleased to report it's possible to run CGNS meshes over 1 billion cells now, so that's no problem. Wall functions, wall models, you saw in the early talks, a lot of work in scale resolving simulations in general, so great progress there. Manufactured solutions, there's a whole framework for that now. So there are many things we can be pleased about, and I can't list them all here, so I don't want any developers to feel bad that their work's not put up here, but we can be proud of a lot of things. We've put in a lot of effort as a team. Now, on the other hand, there are some things that we're just not quite there yet. So these are those repeat offenders I mentioned. So the first few are things that are also on the successes list. So robustness and convergence. I mean, look, this is something that is never going to be finished. So we need to keep working on it. We are aware that folks are having some issues still with meshes that maybe have low quality cells or highly stretched anisotropic meshes. We know there are still things we can do to improve. So we hope we can talk about that a little bit here today. Okay, so interfaces to external packages. This is sort of the same thing. This is probably something that will never officially be finished. We just need to take the pulse of the community, see what packages people want to interface with, and organize our work in that direction. Similarly, more documentation and tutorials, validation databases, these things will also never be finished. We just need to keep doing our best to keep the documentation updated, add more test cases, do a great job to compare to experiment, and take validation cases from the other communities in different application spaces. And then there are some technical things that keep slipping through the cracks. So things like multi-grid improvements, so both FAS and agglomeration multi-grid, mesh generation and integration with SU2. This is an area where we always get requests. We always are asked, how do I generate meshes for SU2? Do you offer us anything to generate meshes? Can you do it automatically? Which to this point, we haven't tackled as a community directly, although we have some collaborations in that direction. And then, of course, people want more physics and more solvers. Pretty much always. There's always more to add new models. So go ahead and hit next on the next few bullets, please, Juan. So things like MHD, which came up in this conference again, we actually had it listed in our priorities from previous years as well. Lattice-Boltzmann methods come to mind, transition models, which we talked about, multi-phase flows, others, so maybe particles, Lagrangian particle tracking, things like that. We need to do a lot of work on the shape optimization framework. We're aware of that, and we're actually already starting, so we might have some comments about that. Shape parameterizations always need attention. We've been using a lot the freeform deformation approach, but it could be improved and expanded, and I think there's a lot of room for improvement there. Multi-zone parallelization is still a little bit of a sore spot, and another one that comes up is graphical user interface. That always comes up, but it's hard for us to actually work on that topic, so we'd love volunteers to talk about that. So I just want to stop here and for a moment highlight the fact that we can always improve. So the things on the right, of course, we need to get to. These things keep coming up, and I view them all as opportunities rather than big issues. And I just want to make sure we're all sort of having a positive light here, and remembering that while we can always improve, we should really take the time to celebrate all the hard work of the folks in the volunteer community. So all the things in the left column that people are working on, remember that these are people that are volunteering their time. They're working as maybe students to develop work for their PhDs, or they're just in their free time, improving the code, working hard, putting in a ton of effort. So I don't want to put too much negative emphasis on things. This is also a chance for us to sort of celebrate that hard work and be very proud of what we've done, as a volunteer community, helping each other out. So let's not lose sight of that. Okay, next one. So now I'd just like to point out a few areas where we know folks are already working, and this is probably not a comprehensive list, but the idea here is just to give folks in the audience some idea of ongoing projects that we know about. Yeah, you can just animate them all. Thanks. And these are areas where we already kind of have some points of contact in mind, and many of you are in the audience, you'll recognize these topics. And so, be prepared. We can maybe talk in a little bit when we get the discussion going. We can have you unmute and maybe say a word. But these are areas where we know folks are actively working right now, and we expect a lot of work to be done in the next year. And there are also things that we probably don't know about. So this is a chance, if you're watching and you guys are working on something in the code base that's maybe not apparent to us, either through discussions or on GitHub, if we haven't interacted yet, then I encourage you to get involved on GitHub. So go and maybe tell other folks on GitHub, or open a draft pull request with your work, so we can start the conversation about what you're working on and how to integrate that into the code base. Or if you're here in the chat, in the GoToWebinar call, you can always just leave us a comment in the question box and let us know if something's being worked on, maybe leave your information, and we can make sure to connect you or bring you on here for some discussion in a few minutes. And so without going through the whole list exhaustively, I think based on the talks you've seen the past 2 days, I think it's clear what some of the folks here are working on. So things like the high order solver, scale resolving flows in general, so both the finite volume and the discontinuous Galerkin solver. A lot of things for outputs and shape optimization, and the framework in general that is going to be improved. We've had a lot of discussion about that. Like I said, performance improvements and convergence acceleration is really never done. So you can imagine a lot more work needs to be done there, and will be done there. And just to highlight a few others, unsteady optimization, pressure-based incompressible solvers. We saw Akshay's talk yesterday, which wasn't specifically about pressure-based solvers, but we know that there's a lot of interest there, potentially for more work with combustion as well. So like I said, if you have other topics that you want to bring to our attention, either drop a note in the question window so we have an idea, or if you already have some work in a branch on GitHub, for instance, go ahead and just submit a draft pull request. Even if you're not even quite ready to integrate it, you just want to let the other developers know what you're doing, maybe get some feedback. It's a great way to start that process. Okay, let's go to the next one. Yeah, as I said, if you want to be a point of contact, just let us know. Okay, so now we're at the point where we would like to attempt to do some polls. So let's see how this goes.
So my audio should work now if you can hear me, so I can help you out.
Excellent, perfect. Okay, yeah, you want to jump in, Juan? Because I think you're going to drive the polls.
Sure, I'll be happy to. So let me just share the screen from this other computer, so it's a little bit easier.
Okay, so the idea here is we've prepared, while Juan's doing that, we've prepared some several key areas where we want to solicit your feedback on priorities. What you see is, basically a high priority for your needs, or things that you're really interested in. We should say a lot of these topics folks are already working on. There's a lot of work already happening, but we want to get, sort of the pulse of the community so that we know kind of what folks what resonates the most with people, and how we can kind of focus our development over the coming years. So, hey, Juan.
Yeah. So we prepared 6 polls for all of you to sort of give us a little bit of feedback as to how we should direct our efforts as a community over the coming year. And as Tom mentioned earlier in the discussion, what kinds of things you would like us to all be talking about next year at an annual conference that hopefully will take place in person. So we'd like to give you a little bit of an idea of what these polls are going to be about, so you get the rough categorization and the various different elements that are in there. So there's 6, as I mentioned, and we'll start 1 through 6. The first one talks about issues related to the numerical methods, basic discretizations, robustness improvements inside of SU2. So again, a lot of things that we talked about through the years, but if you select some of these things, we would like you to sort of give us the feedback saying you think that if it's being done, we need to do more of. If it's not being done, we need to put it on the list of the things that we're actually working on. So you see things like linear and nonlinear solvers, new preconditioners, algebraic multigrid, higher order discretizations, which include a lot of effort in DG at the moment, but maybe other things within the finite volume solver, the ability to be more robust to different transients in the initial solution, but also to poor grids, to anisotropically adapted grids, which there'll be a talk on afterwards, and then also just sort of investing effort in advanced discretizations. The second large area that we want to ask you about and we want to engage you on is this idea that physical modeling should continue to improve within the SU2 framework. And you saw a little bit about the beginning of simulations on scale resolving methods, but there's flow transition. There are a lot of things in high speed, non-equilibrium, real gas effects, reacting flows, combustion modeling, wall functions, various other things. So the third one that we want to put up here is this issue that those physical models and all those new capabilities, the larger grids, so on and so forth, are always enabled by high performance of the code. So obviously there's already a hybrid MPI OpenMP implementation going, but there could be improvements to that. There's the possibility of a GPU implementation. We don't know of anybody doing that at the moment. Better setups in the memory layout in the code, reordering, vectorization, so all going into faster single processor performance. And then, we've also put in the idea that while we have a number of different validation and verification benchmarks, we often don't talk about performance benchmarks and whether we should start one of those in order to sort of understand where hotspots are and where we can do better. And then in the category of performance, we've also thrown in, large mesh improvements, so being able to deal with much larger calculations. We've had a number of fixes and pull requests recently, but we are getting to very large meshes now. So the fourth category of the poll is going to be multiphysics and interfaces. So this is the idea that it's not just a CFD solver, but we're beginning to couple with many other things. So fluid structure has been going for a while, and we can do many more things there. Conjugate heat transfer is another big thing. There's sometimes the need to have various different bodies moving in relative motion to each other. So unstructured oversetting may be useful. In fluid structure, there's a lot of talk about coupling with external solvers like TAX, an open source structural solver from Grand Kennedy at Georgia Tech, but also Nastran, both in the MSC and NX versions, electromagnetics, so on and so forth. So those are the options that you're going to be seeing. The next to last category is adjoints and optimization. So, we rely heavily, particularly for 3 dimensions, on using our freeform deformation boxes, but are there other shape parameterizations we should be looking at? Should we expand radial basis functions? Should we have better connections to CAD, right? There's a lot of discussion about optimization methods, whether there are additional optimizers that are gradient-based optimization methods, but also, non-gradient optimizers. There's the potential to improve our automatic differentiation basis for all the adjoints and doing things that lead to additional robustness. And I think Nico mentioned this briefly during the first day. How we deal with geometric constraints? Is there a way to formulate those in a more generic way? And then finally, better mesh deformation approaches that are more robust in the context of optimization. And last but not least, there's this sort of category that we call code-based support, where we have a lot of things that are really important to make sure that the community thrives. So better code integration, unit and regression tests, validation and verification, including a database that we've talked about and we've done a little bit over the years. Better documentation, better tutorials, more events, maybe at the developers meetings, to train people, more reach out things, more videos on the website that could actually help people get up to speed more quickly. And then finally, this idea that people want to automate lots of tasks. So we have a nice Python interface already. But we really would like to see if that Python interface can actually be enhanced, and many tasks, whether they're better optimizations, but uncertainty quantification, sweeps, and various other things, could actually be automated. So Tom, with those 6 blobs, what we can do, if you don't mind, is we're going to begin just going to one blob at a time. So we're going to bring up these different polls. I'm going to start with numerical methods, and now I'm going to launch the poll. Each poll will give you 5 options. You could cheat and select all 5, but that's not the spirit of what we actually want to do. We're asking people to select 2 choices per poll that represent, the highest priority for that specific person. Only the attendees are able to do these polls. The panelists will not be able to reply to these. So let me just launch the first poll, which you should now see on your screen. It's related to numerical methods and robustness. And again, all the attendees, if you don't mind, go ahead and start clicking of those 5 options, the top 2 that you think the SU2 community should be pursuing in this particular category. And we see all the people already voting, which is really nice. We see it here dynamically. There's about 40% of you who have already voted. And as soon as we have another few seconds go through, we'll stop the poll. So vote quickly if you want to. And then we'll share those results with you. So we have a very engaged audience. Already 60% of the attendees have responded. I'm going to give 10 more seconds. Yeah. I'm going to give 10 more seconds, and then we'll stop it so you can all see what's actually going on. So again, you're not simply voting for things that we're not doing that we ought to be doing, but things that we are already doing and that we need to continue to do well and to do more of if possible, right? So I'm going to stop the poll right now. I guess 65% of you have voted. And let me just share those results with you so you can actually see what's in there. We're not going to do a lot of analysis here, and Tom, but I think this is very useful data that will frame the rest of the conversation. So that's poll number 1. You can see that I guess robustness is important, and linear solvers and nonlinear solvers and preconditioners are quite important. So we'll continue that. High order discretization occurs 3rd. So let me throw up the second poll, which in this case is going to be about physical modeling. And again, we're going to give you a minute to fill out that entire poll. So go ahead and click away as to what you think are the most important things to pursue in physical modeling over the next year. Of course, these are sustained efforts that have been going on for a while now, but we are quite interested in your opinions. So again, 20 more seconds, and then we'll stop the poll. Already 60% of people have voted, which is amazing. Thank you for being so engaged.
Yeah, that's great.
5 more seconds. So, you haven't made up your mind. Go ahead, do that, please. And here we are. So let me close that poll and share the results with you. So you can see that it's a bit of a mix, but definitely scale resolving simulations is probably in the lead. And then of course, there's a lot of interest in the other various different areas. So again, we'll take this into consideration, but in the interest of time, so we have lots of time for discussion, let me just keep going. So The next poll is about performance, and we said here focus on strong scaling because that's typically the uses that we see in SU2, but you know, it's not only restricted to strong scaling. So go ahead, vote for the top 2 of the things that you want to see there. And I have to say, by seeing the results, not many surprises.
Yeah.
Again, almost 60% of people. You guys are amazing at responding very quickly, so we don't have to spend very much time doing this. So I think 3 more seconds, and then we'll stop. And let me show you now the actual results of that poll. So we have hybrid open MPI, GPU, very unsurprisingly, and then the other 3 very close to each other. So excellent there.
Yeah, that was pretty even.
Yes, that was pretty even, right? So let's go to the multi-physics and interfaces. Very curious as to what you guys think are the top things we ought to be doing. I'm sure there are others, by the way, and while you're voting, Tom has mentioned this before, but in either the chat window or the questions, if there are things that you don't see in many of these polls, please throw them in, because we will put together a survey for all of you for after the conference, and we'll add those new things into there. So, all right, we're at 60%, so 5 more seconds, and then we'll show you what is actually going on. And let me share those results with all of you. So now you're seeing fluid structure is certainly a huge thing. Then you see the next 2, and then Nastran and TAX and electromagnetics as a sort of lower end. So 2 more, adjoints and optimization. So please do the same thing. Top 2 choices. What are the things that you'd like to see more work on during this particular year? So again, the votes coming in very quickly. I'll share those with you in about 10 seconds or so. We're at 50%. And 5 seconds, and we'll stop. So let me show you those results. Very interesting as well, Tom. I don't know what you think, but obviously shape parameterization is something we need to continue to pursue. A lot of mesh deformation approaches to go with those new shape parameterizations, and then optimization is good. Then last but not least, this is a really important one, although you know it's probably the last thing people want to work on, but please go ahead and select, just like you've done, the top 2 among the 5 choices that you're actually given here. So again, better code organization. It's always useful to get people going, units and regression tests, VMV, more documentation, tutorials, so on and so forth, and events, and then sort of a better interfacing with the code to automate various different tasks. So we have 65% voting, so 5 more seconds, we'll stop right there. And let me just share with you what the results of that poll are. So obviously, Tom, a lot of interest in documentation, tutorials, and organizing events. So as we have bandwidth to do that, we probably have to pay quite a bit of attention to it. So
yeah, I think that's the most clear one so far.
Yes, let me just sort of wrap this up, Tom, so we can start a bit of a discussion. So we like to track our progress. We like to get communities working together. We like to make sure that sort of GitHub projects are you know, used like you see in the right for the folks working on robustness, performance, scalability, and VMV. There are other projects in there. There are things that we could attempt to expand if people think that they've been useful. So we like people to chime in all these different areas, right? So. And finally, Tom and I often get requests about people who want to teach a CFD course using SU2. And the first thing that everybody asks is, has this been done before? You know, are there materials that we could inherit in order to prepare such a course? You know, how does it work with students? So on and so forth. We used to have a version of the code, SU2 EDU, which by the way still works, which is a stripped down version of the solver that is a very good vehicle in order to actually teach people how to learn CFD and how to write CFD codes, et cetera, et cetera. So we could connect with all the people that are interested in doing this. If you're interested, reach out to Tom and to myself or to anybody else in the foundation board. So Ruben, Tim Malbring, and Eran Arad, and we'll be happy to do something about this. There's been a lot of interest at various different institutions, and courses have already been taught in multiple places, right? So we'd love to be able to facilitate all that. So in sum, we want to open this up for discussion, but we want to make sure that you understand that our mission is to continue research, to continue to produce tools that benefit everybody. We like you to be involved because this is a volunteer organization. Everything we've done is thanks to the kind efforts of many people and institutions around the world. And we'll leave you in the slides here just with the thought that you ought to join the email list that we have. You can also get in on the action at GitHub. And then, of course, you can contact us about anything at the info@su2foundation.org. So Tom, what do you think if we start opening this up for discussion? Maybe we can invite some of the folks that are in the panelist list if they want to say something about priorities to just come on board. And I'm going to be looking for some of our attendees that may also have something, and I'll promote them to panelists. So take it away, Tom. Mm-hmm.
Yeah. So I would say, as Juan just said, anybody here that's already logged in as a panelist, if you want to jump on and comment, please do right away. There are, in the meantime, a couple of questions on the question board here. I'll just bring those up since we're kind of transitioning, waiting for people to jump on. So just to say a few things that appeared in the slides. People have also asked here today, any plans for GPU computing? We saw a lot of interest in that in the poll. There's interest in finding out who else might be working on multi-phase flows. So this question comes from TU Delft, and they're wondering if anyone else out there is interested in multi-phase flows or working on multi-phase flows. So if you are, you can either leave a note in the question box or try to virtually raise your hand. We can try to bring you into the conversation.
Yeah, so I think, Tom, I've unmuted a number of different panelists and I promoted a few people. So if they want to talk, they can unmute themselves. But I think it'd be nice to hear from them if we've left some things out that are really important for SU2 to continue to thrive over the next year. So if anybody wants to go, please feel free to also share your webcam and just say something. So.
Hi, Juan. I would like to say a few words.
Yes, please go ahead, Eran.
Great.
Well, besides this great beginning that you started, I think from the polls you can see something that is really bugging us for a long time. The base understructure of the software is one of the places that require some attention. And actually, today I think we received, or yesterday, a mail from NASA asking about our involvement in infrastructure improvement and the crucial importance of that. And may I mention, actually, we started the foundation for this purpose, to enable some not so attractive or top scientific work to be done, but which is very necessary. And this is exactly why we exist. Hopefully we'll be able to be supported somehow so we can invest some of the funding that we have in this infrastructure to the benefit of everyone, because otherwise people at their choice take the top interesting subjects, which are very important, but are not infrastructure. And I think the polls actually supported that the community is also aware of these necessities.
Okay. Yeah, no, thank you for saying that, Eran. I completely agree. So thanks for the comment. I think there are, the basic scaffolding of the code and how it interacts with many other things is just critical. And making sure that everything works as advertised, that it's robustly doing what it's supposed to be doing, also very critical. So, Tom?
Yeah, couldn't agree more. Very well said.
Yeah.
So thanks for bringing that up.
Anybody else, go ahead. And if you're an attendee and you have something to say, please post the question. And we are trying to say things here. Let me see.
We are getting quite a few, so it's a little hard to. I don't want to just read directly the questions, but I'll try to cherry pick a couple that maybe we can have some conversation about.
Sure.
So it did come up again here on the questions about having courses based on SU2. So someone proposes that it'd be nice to have a network of academics who are doing this, and we'd be happy to facilitate that. So if you're interested, maybe leave a comment here in the question box if you are interested in that. And we, as the foundation, will collect those names, and we can send out an email afterwards, connect you all if you don't already know each other, and we can start that conversation.
Tom, there's a question about turbomachinery, and I think Matteo and Piero and even Nitish are in the panel. So if anybody wants to say something about that, please feel free, because there is quite a bit of development in that area, and I think there'll be a presentation later today. So. So could I invite?
Yes.
Yep.
Do you hear me?
Sure. Yes.
Hello?
Yes.
Let me see if I'm able to.
Matteo, we can see you.
We can see
you.
Hello.
Yeah, there will be a presentation from Nitish, so from one of our PhDs later, also regarding new ways of shape parameterization methods for turbomachinery applications that can actually be extended also to various types of applications in the engineering field. So I think folks could find that interesting, and we will, if there are any questions, please feel free then to forward us. So to me, Pierre, and me.
Yeah.
Thank you, Matteo.
Maybe just to add.
Yeah.
Sorry, just to add over that, I think there's also a lot of interest for the different kind of optimization algorithms. So we also have a code which kind of, wraps the SU2 with this parameterization method, but this is capable of using, let's say, packages from, let's say, Pygamo, which is a library managed by AASHA, and also it's also, let's say, it's coupled with the SNOpt, so it can also use the SNOpt library for optimization purposes. So, well, I think if there's a lot of interest, we can discuss with the foundation to integrate it along with SU2 in a more seamless manner.
Juan, I didn't see the question. Was there a specific question about turbomachinery?
Yeah, there was somebody said, well, there are two questions that I saw, and one was, what's the status on turbomachinery capabilities, non-reflecting BCs, phase lag, boundary conditions, et cetera, et cetera. The other one was also a little bit more general, right? I wonder how many turbomachinery groups use SU2, and do you have any idea? So, but we can move on. If you guys have something to add, please feel free.
Yes, some of this information will be also showed by Nitish.
Exactly.
Right.
Good. Great. Yeah. Again, I'm interested in anybody thinking of other things we haven't talked about. I'm seeing everything through the list here, Tom. I don't know if you're looking there as well, but there's an interest in putting together a network of academics who are interested in teaching based on SU2, and I think we can certainly facilitate that. So.
A couple more comments about external optimization packages, links to things like OpenMDAO, which has come up now a couple times.
Yeah, Arturo, who presented yesterday, is asking about people in the community who may be interested in doing transition models. So I would encourage to have people contact Arturo Cajal, who is at USC, and his advisor, Alejandra Urganga, who may be very interested in collaborating with you guys.
And on that one, I would say there's already some work open on GitHub, so let's bring the conversation there for both Arturo and the other folks who are working on, let's say, scalar transport equation models. So we can have a good discussion there.
So Tom, we have barely 1 minute left in this session, so we don't go out of schedule. But I would say that we are very interested in people's suggestions, questions. So please reach out. You have the information on the screen on how to reach out in many different ways. we will put a survey together for people to fill out, where you'll be able to put in some of your ideas, just like you've done in the question box. And we'll take all that into consideration, and we look forward to discussing something like this in person with more time, hopefully next year.
Yeah, and I would just add, feel free to keep adding things to the question box. We're going to save all those and export that, so we'll have all your comments and questions. So don't feel like it's lost to the void if you've said something and we didn't comment. So please keep sharing. Okay. Well, thanks for that. Thanks for participating and doing the polls. I think, and Juan, thanks for running that. I think that was, great. We got a lot of good data. So, okay, then I think it is time that we go ahead and transition now. So we have today a talk here by Brian in a moment, and then we'll have a break followed by a lightning talk. So kind of a similar format for the rest of the day as we've had the past couple of days. So, well, let's first introduce Brian, who is a student at Stanford working with Juan, and he's going to talk to us today about his work on goal-oriented anisotropic mesh adaptation. And I think you'll all be very interested in this, the folks who are interested in how we handle sort of stretched meshes and what we can do to improve convergence on those meshes. I think Brian has a couple comments about that. So take it away, Brian.
Oh yeah, thanks for the intro, Tom, and thanks everyone for coming to my talk. So like Tom said, I'll be talking about some of the recent developments in the mesh adaptation framework in SU2. And
Brian, if you're not able to switch slides, just ask me for next and I'll do it for you. But you should have control now. Yeah.
Okay, I think I was just muted. But okay. Anyway,
we can hear you now. You're good. Go ahead.
Okay, cool. Yeah. So yeah, I'm not able to go back. But anyway, yeah. So I'm going to talk about the mesh adaptation framework that there we go. That we implemented in SU2, some of the recent developments, and this framework uses the AMG library that's developed at INRIA, mainly by Adrian Loze. So very first, I'll give a brief overview of the talk. I'll motivate why we care about mesh adaptation, and I'm sure most of you already know. Some previous work, both just in general and in SU2 on mesh adaptation. A little bit of theory, so there will be some equations, hopefully not too many for 7:45 a.m. for those on the West Coast. The actual implementation details in SU2, including the framework itself, improvements to the solvers in order to handle these meshes, and then some of the features that are exposed to the user at the moment. I'll give some preliminary results for RAN's mesh adaptation on the RAE 2822 airfoil, and then some conclusions and future work. So like I said, I think most people that do CFD would know why we care about mesh adaptation, but very briefly, we all know that the accuracy and robustness of our high fidelity analysis and design tools are highly dependent on our discretization, and these discretizations are usually handmade or generated automatically, but maybe not so great. And it's also known that mesh generation is a significant bottleneck in the CFD workflow. And honestly, it's my least favorite bottleneck in the workflow, which is why I usually make Jayant and Zan make my meshes for me. But this point is actually made in a more objective manner in the CFD Vision 2030 paper. And for the case of anisotropy, most of the physical phenomena that we actually care about modeling are highly anisotropic in nature. Whether we're talking about the shock wave coming off of the hypersonic vehicle on the left, or the vortices and boundary layer coming off of the wing on the right. So using anisotropic mesh adaptation can drive down the cost of getting high accuracy simulations. Now, when people talk about mesh adaptation in CFD, a lot of times you'll hear about this Venditti and Dharmathal paper where they developed this a posteriori error estimate for functional outputs. So in order to accurately measure some functional, they have this error estimate where you compute the error on a finer mesh, but that can be pretty expensive because generally this requires a mesh that's maybe 2 times as fine in 2D or up to 8 times as fine in 3D when we're talking about triangles and tets. shortly after that, we see the development of an a priori error estimate. So now you can compute error estimates on the current mesh. So it's a lot cheaper. And then the folks at INRIA built on this and developed their continuous mesh framework, which draws a continuous analog to a lot of the discrete elements that we use. And from that, they developed an optimal metric for adapting a mesh in order to minimize error in some LP norm. And then building off of that, Adrian Lozé, who I'm working with on this, developed an a priori functional error estimate for the 3D Euler equations, and then his PhD student, Loic Fraza, then extended that to the Szilard-Almaras equations. And then I recently built on that for the SST equations in SU2. Now looking at the original mesh adaptation in SU2, it was originally very isotropic in nature. So we could either adapt based on some norm of the gradients or adjoint weighted residuals in a similar manner to that a posteriori error estimate. And you get meshes that kind of look like this. So this is capturing a shock wave for flow over a hypersonic vehicle. And this is okay, like I guess it gets the job done, but it also, well, one, it could use some anisotropy to drive down the cost. And it kind of reminds me of this this interview with Tom Economon that I saw once, where he said that he judges the quality of a mesh using the eye test. So Tom, maybe at the end of this, you could tell me if this mesh or some of the other meshes you see actually pass that eye test. Now, when Victorien Meunier did his postdoc at Stanford, he created the first hook between SU2 and INRIA's AMG library. And so we were able to do our first feature-based anisotropic adaptation. For example, capturing Mach contours for flow over the CRM wing here. And this was mostly for inviscid flows. There were some robustness issues to prevent it from working on RANS flows. And then much more recently, I, along with Wally Meyer and Jacob Niedels, published a paper in the Hypersonics conference where we did goal-oriented adaptation for the TNE2 equations for hypersonic flows, which consisted of an adjoint weighted error in Euler fluxes and chemical source terms. So there are two main types of adaptation, which I kind of hinted at the previous slide. The first one is feature-based, which I'm showing here on the left, where we're essentially trying to compute or drive the best mesh to compute some characteristics of some flow solution U. So for example, here we have flow over a supersonic vehicle that commits the cardinal sin of having flow going from right to left for some reason. But we're essentially trying to capture or accurately measure the pressure field. And so obviously we would expect it to capture all the shock waves and then the wake of the aircraft. But if you're interested in measuring a specific output like lift or drag, then you'd be more interested in goal-oriented mesh adaptation, where we try to derive the best mesh to compute some functional F of those flow variables U. So for example, here we have the same vehicle, but we're trying to measure some metric that, I guess, some measure of loudness at the ground. And so naturally, we don't really care about what's happening above the aircraft, and maybe not even so much about the wake. We just care about the shock waves that propagate to the ground. And whichever framework you use, whether it's feature-based, goal-oriented, a priori, a posteriori, in order to get anisotropy, we need this notion of a metric space, which I'll describe briefly here. So in our finite volume method, we assume we have piecewise linear elements, so essentially constant gradients in our elements. And so naturally, we treat our error as second order. And we want to define a Riemannian metric space, which means that we have this space that's defined by a tensor at each point in the domain. And that metric space is governed by our error. So since our error is second order, we use Hessians. So for example, in 2D, our metric space M at each point X is given by the Hessian of some quantity of interest at those node locations. And when we actually do the mesh optimization, what we're trying to do is determine the optimal locations of our nodes in order to drive down the error, or rather equidistribute the error throughout the domain. So we need some notion of an edge length in this metric space. So to give a more simplified example, just to kind of illustrate some of the anisotropic properties of this metric space, I'm just going to show a case where we have constant M in space. And so our edge length in this space is just given by the norm in that space. So you can imagine that if M is the identity matrix, we just recover the standard definition of a Euclidean distance. And if we expand that equation to the form on the right, we see that the components of our metric tensor correspond to the coefficients of an ellipse. So a lot of times you'll see people visualize these as ellipses. So in order to equidistribute the error, we want a constant length in this metric space. And so if we just set that to 1, then what you'll see is that the eigenvalues of our metric tensor are inversely proportional to our desired lengths in the output mesh in those principal directions. And I think this makes a bit of sense, or a lot of sense actually. So if you think about it, if we have like a shock wave, for example, most of our variation is happening normal to the shock wave. And so we would want most of our refinement to happen in that direction. And so you'll see elements that are stretched along the shock wave. In reality, and I won't go into detail about this, the edge length is a little bit more complicated because the Riemannian space is a continuous space. So we actually have to integrate these metrics in space in order to perform our mesh optimizations. And that's all handled in AMG. Now, I mentioned this before with the optimal metric, but we have this discrete continuous duality in this continuous mesh framework. So for example, the continuous analog of our elements K is our metric tensor M at each node, or throughout the domain rather. The mesh X is related to the Riemannian metric space itself. And then this one's going to come up on the next slide. The number of vertices N is related to this, what we call a mesh complexity, which is the integrated density in this continuous space. And this is what we actually control in our framework. So the optimal metric is a normalization that we perform in order to minimize the error in some LP norm. Like obviously we have to perform this normalization because if you think about it, before we were just computing Hessians, but the scale is kind of arbitrary, very problem dependent. So I have this equation here, which I'll break down really quickly. So this is the optimal metric derived by Frédéric Alauzet. The first term is the desired output complexity. So this continuous analog to the number of vertices that we want. So if you want to refine your mesh, doubling N typically doubles the number of vertices, but you won't typically match the number of vertices exactly. The second term is a global normalization that we perform in order to reach that desired complexity. The third is a local normalization that we perform in order to damp out small amplitude variations in our metric space. And so we have two free parameters here, N, which is what we use to drive refinement in the mesh, and then P, which is a choice that I'll describe briefly here. It's our choice of norm, which is mostly dictated by the problem. And larger P's tend to damp out small amplitude variations more. So if we look at this sample function here, which is just a sinusoidal function in 2D space, a slice at y equals 0 is shown here on the left. Then if we adapt a mesh for that function for p equals 1 versus p equals 4, we see that p equals 1 tends to adapt more in the small amplitude regions. And Loic Fraza basically suggests in his thesis that p equals 1 or 2 works well for Euler for mainly capturing shocks, and p equals 4 works well for RANs, where we have different scales in our flow that we need to resolve, and we want to damp out other features. So in order to get into the viscous error estimate, I'm going to motivate a little with how we do the inviscid error estimate. And this is what I, Wally, and Jacob did for our TNE2 paper at the Hypersonics conference. So we approximate our error by linearizing about the flux terms and then also chemical source terms in the case of TNE2. So our residual is just the standard form of this divergence of fluxes minus our source terms, which is hopefully equal to 0. And we assume that our error is an adjoint weighted interpolation error of these terms. So H denotes a discrete quantity and U bar denotes our adjoint variables. And we want to extract a linearization about F and Q. So Q is already in the right form, but in order to get F, we integrate by parts and neglect boundary terms. And what we get is this here. So now we weight our errors of our Euler fluxes using gradients of adjoints. And so now we have an error estimate. And like I said, we're using Hessians to approximate our error. So we take Hessians of these linearized terms. So we have this adjoint weighted Hessian, which is given by these gradients of adjoint variables weighting Hessians of each of our Euler fluxes and adjoint weighted Hessians of source terms. And then we perform the LP normalization that I described before. And this works all right for the Euler equations and TNE2, but it doesn't properly weigh errors due to gradient terms, such as those that you'll see in like viscous and dissipative terms. So in Loic Fraze's thesis, he describes this viscous error estimate where we instead linearize with respect to the conservative variables. So now we have to essentially get our error estimate in this form, which means that we need our Jacobian, which we already have, so that's fine. And we need to manipulate terms of the following forms. The first I call 0th order terms. It's like the source terms that we saw before. The second are these, what I call first order terms, which are like the convective terms that we saw before. So we already have a way of linearizing these. It's just a slightly modified form. And then the third terms are these second order terms, which come from the viscous terms. And so in order to linearize these, we basically just, once again, neglecting boundary terms, we integrate by parts twice. And so now our error estimate with respect to our conservative variables is this Hessian of adjoint weighted error. And these terms W and all these terms come from our Jacobians, which, like I said, we already have in SU2, so that's easy enough. And just to kind of give a brief example of how we do this, if we look at the error due to the divergence of heat flux in the energy equation, we have this Laplacian of temperature, which we can decompose into like a Laplacian of energy and a Laplacian of density. And if we integrate by parts the adjoint weighted error of that, then just looking at the energy term, we have this Laplacian of adjoint energy that weights our interpolation error of our actual energy primal variables. And so in compact form, we have this adjoint weighted Hessian that's composed of these 0th order, first order, and second order weights as shown here. And then once again, we normalize that to obtain the optimal metric that I described. And in order to do this for SST, which is kind of a messy equation, I made some simplifications. So these blending functions I treated as constant because I just assume that they don't really do too much, like contribute much to the error. They're just kind of used to switch between K epsilon and K omega. And quite honestly, I didn't feel like linearizing with respect to hyperbolic tangents of like inverse of cross diffusion and all that nonsense. I don't treat the limiters on shear stress or production, so I don't really treat these maxes. I just use a simplified version of these terms. But then I linearize with respect to everything else in the equations of motion, including viscosity and thermal conductivity, which helped me later to implement actual Jacobians for these terms. And that leads into the modifications that I actually made to the Navier-Stokes solver and SST solve in order to get these flows to converge. Because like I mentioned, when Victorien Meunier first implemented his mesh adaptation framework, he had some robustness issues with specifically RANS flows. So one, I store the conservative turbulent variables because while in master and develop, we store the primitives and our adjoints are with respect to the primitive variables. Our error estimate is actually in terms of the conservative primal and adjoint variables. So I just store these extra variables in this variable structure. I got rid of the solution clipping, which seems to kind of be a band-aid for a lot of other problems in the SST solver. And instead I use under relaxation, which seems to work fine with all the other modifications that I've made. I got rid of the omega production limiter just because I think that extra specific dissipation kind of helps with convergence. So our wall boundary condition for omega is given by this equation here, where delta D1 is, as described in the original paper, your distance to the first off-wall node. And in SU2, we use what we call the normal neighbor and the distance to that node. But for my highly anisotropic meshes, like the one shown here, where this is an element adjacent to the boundary, that distance doesn't really give an accurate representation of what omega should be. So since this equation is based on boundary layer theory, and so I instead used the actual wall distance to that node. I won't really go into detail about this, but this thesis shown here kind of describes this more stable version of a gradient correction at our interfaces for our viscous fluxes, which I implemented. And then I basically linearized pretty much everything that wasn't linearized before. So I only did it for green gas, but I linearized the actual gradient computation routine, whereas before we just linearized the gradient correction terms at the interface. I linearized the production and cross diffusion terms, and then all the viscous and heat capacity terms. So onto the actual framework itself. Essentially, we just have this adaptive loop where we run a flow, adjoint, and metric computation in SU2. The metric computation is just a post-processing routine in the adjoint driver, and it's just computing those adjoint weighted Hessians of our conservative variables. And then I have this external library, which was mostly written by Victorien, and then I just converted or made it into an external library. It essentially just converts from SU2 format to the gamma mesh format, which is what's actually used by AMG. AMG performs the actual mesh adaptation based on this metric and then interpolates the solution onto the new mesh. And this whole process is repeated until we converge our problem. And if anyone wants to run this today, there's a stable in quotes branch in the feature adapt branch. I wouldn't recommend running the RANS stuff yet, as that's highly experimental. But if you did want to run, for example, Invisid or just like Hessian-based mesh adaptation, I'm going to describe some of the options available. Currently, PyMG is limited to triangular and tetrahedral meshes. So if you do this, then make sure you generate a mesh that's tris and tets only. You can specify what's known as a background surface mesh, where we basically have this fine representation of the surface. And even if you're doing RANS, this can be an Euler mesh because AMG just uses it to generate a P2 and P3 approximation of the surface. It can be an SU2 or GMF format. And if you don't specify a mesh, it just defaults to the initial mesh that you use. You can choose whether or not you want AMG to perform ridge detection. So it basically detects important edges and corners in your geometry that it should try to preserve. If you don't want to use ridge detection, at least for the case of 2D, I wrote a Python script that takes the intersection of markers in the mesh and uses that to determine corner points. So in this example mesh here, I had an airfoil that was split into an upper and lower surface, and so it detected 2 corners. And I just append these 3 lines to the end of my mesh file. The user can obviously choose which type of adaptation they want. If you specify goal, then you need to define an adjoint problem. Target complexities, which is this idea of mesh size, or roughly proportional to the mesh size. And so usually I pick the first value to be about the size of the mesh, and then increase, or the initial mesh, sorry, and then increase from there. The number of actual adaptations to perform at each mesh level, the norm that you choose to use, which just to illustrate what this might look like in SU2, the K omega model is known to have significant drop off in K and omega at the far field boundary. So P equals 2 might refine that a lot more than P equals 4, which, like I said, higher P damps out small amplitude variations a lot more. Maximum cell size, this is just to prevent the mesh from getting too large at the far field. Minimum cell size, which seems to be more important for RANS, at least for SST, if I let this get below like y+1, then I would see divergence a lot of times. Gradation parameter, which is used to smooth the mesh by capping the maximum ratio of neighboring cell sizes. So for example, here I'm showing hgrad equals 1.5 and hgrad equals 3. And so you can see that the gradient in cell size is obviously larger in the case on the right. And 1.5 to 3 is about the range that Adrian Lozé recommends for CFD problems. And so I'm just going to briefly highlight some preliminary results on the RAE 2822 airfoil, which is pretty standard test case. And my initial mesh had about 30,000 points, look like this. I tried to adapt my mesh to compute lift coefficient accurately. I doubled the mesh size 3 times, and just hmin based on y+=1, hmax is not too aggressive, and then hgrad. And here I'm showing some convergence plots for one JST and then also rho on the right here. And you can see that rho performs better in general than JST, which I think shouldn't surprise anyone familiar with the scheme because of the artificial dissipation present. So I think that affects 1, the metric itself, and 2, just the solution quality. So comparing rho for p equals 2 versus 4, we can see that they both tend to the exact solution, which is given by this dotted line up here. But p equals 2, at least in this case, tends to perform a little bit better. But I would still say that that p equals 4 from Frazo's thesis is a decent rule of thumb in general. And looking at the actual flow contours and meshes themselves, here I'm showing CP contours. And as you can see in the mesh, we're capturing the shock wave, the boundary layer, the wake, and even the stagnation point pretty well. And if we show Mach number, we can see the boundary layer and the wake actually captured in the flow itself. And then I just wanted to highlight in the region where the shock meets the boundary layer, we can see that we get a good mix of length scales that are captured pretty well. And also it's even starting to capture this oblique shock that comes off of the boundary layer just forward of the normal shock wave. So in conclusion, I implemented error estimate and goal-oriented mesh adaptation for the Euler equations, the TNE2 equations, which I didn't really show here, but if you want to see more of that, then you can look at the paper that we published in the Hypersonics conference, and most recently the SST equations, and demonstrate the ability of this framework to work for viscous turbulent flows on the RAE 2822 airfoil. And finally, the modifications I made to the SST solver and the Navier-Stokes solver seem to have improved some of the robustness issues that we've seen before on highly non-orthogonal meshes. Future work for the project, one, a more thorough investigation of the effects of some of the parameters like the norm and gradation parameter. The norm in particular, just because I was seeing better results with a lower norm in Rand's mesh adaptation, which somewhat contradicts what Frazo suggested, but I think that might be more solver dependent than anything. Implement error estimates for other models, Splart Almaras, which could just be based on Frazo's error estimate, incompressible, and then some of my colleagues and I have talked about implementing a wall function based adaptation framework in order to further drive down the costs. CAD based projection just to get a more accurate a more accurate surface to project our meshes onto, and then further down the road, mesh adaptive shape optimization. And none of this work would have been possible without Vic or Loic for their help with the actual implementation details of the mesh adaptation framework. Wally and Jayant just for general help and also helping me run some cases. Marco for helping me debug the AMGIO library for some of the work that was shown in in Katerina's presentation rather, and the SU2 development team in general. And with that, I'll take any questions.
Great, thanks, Brian. The work's coming along very nicely. So you do have a bunch of questions. So why don't I read a few out for you? Let me back up. There was one earlier today that I think you could say something about, which is how are you handling the geometry at the surface? So you mentioned this a couple times. So I think INRIA tools take in a fine grid, but can you talk a little more about that and maybe CAD, which is your future work?
CAD is, well, yeah, so I'm not really too sure how the CAD implementation would actually happen. I know that we've talked about some libraries like GE Light and stuff before, but yeah, the actual surface mesh that we use, AMG basically takes whatever you provide as the background mesh, and it somehow, I don't know if it's splines or what, but it generates a P2 and P3 approximation of the mesh. And then when it actually performs the mesh adaptation, if it needs to refine the mesh, then it projects points onto the surface on that fine mesh, as opposed to the coarse mesh where you might have where you will have linear elements in that region. So it's just a better approximation of the surface.
Okay, sounds good. Okay, there are a few more questions. So somebody asked, when you're speaking of linearizing, are you doing it by hand or using AD?
I did do it by hand. I suppose that we could use AD, but I think that the treatment of some of those higher order terms where we have to do Hessians of our adjoint variables, I guess I'm not quite sure how we would get that from AD. So, and I did try just doing an adjoint weighted error in the conservative variables at one point, and that seems to give some pretty trash results. So.
I see. Okay, a couple more things. So someone's asking, is the refinement carried out sequentially? By that, I guess they mean, can you do this dynamically during a calculation? So can you be adapting during solution convergence?
So currently it's, yeah, it's done in between solutions. It could be done during solving, I guess. Like it would just require a lot of implementation. It would probably require the use of the Python interface and then some modifications so that we actually like redefine our classes based on the new solution. But one of Nico's PhDs actually had an adaptive one-shot optimization framework that they developed where they were adapting during solution. So it's something that could be done, just not with the current framework.
Yeah, I think it's quite a bit of effort. You need, yeah, the one shot with the adjoint while you're running, and also probably a lot of changes to the data structures in the mesh classes, so you can handle the variability. Okay, maybe just one last one while we transition, or maybe one or two. We do have a little bit of break, so let's just take these last one or two. So someone asks, what happens in AMG if the flow has a small separation or a small shock fluctuation? And is it okay to assume a steady solution within the iterations?
Okay, so yeah, my stuff is currently implemented for steady. And so if you do have a transient solution, some of the folks at INRIA have developed unsteady mesh adaptation frameworks where you essentially compute your metric field at each time step, and then you have some like intersection of your metrics in order to determine your optimal unsteady metric to properly capture all of your features throughout the time history. And I don't have that implemented at the moment. So yeah, if you do have some fluctuations or like a highly transient problem, then it could cause some issues. And I've kind of seen a little bit of that, like sometimes when you perform the adaptation at like a coarser level, the shock might be in a different location than if you've performed more refinement. So it'll have to kind of adjust the mesh as it goes.
Tom, I had a question also that's been sent to me. Brian, you've been talking a lot about the TNE2, which is a thermal non-equilibrium to solver a Shank-Copeland, right?
Yeah.
But we heard on the first day of the conference about the SU2 NEMO. Is the adaptation ready to work with SU2 NEMO already, or are there any steps that need to be taken in order to facilitate?
So they've already done feature-based mesh adaptation with NEMO, which Katerina showed in her talk. So they adapted based on Mach contours. As for the actual adjoint weighted adaptation, I think that, well, we would have to actually get Jacobians with respect to whatever source terms exist in mutation plus, I think, which I don't know how easy that would necessarily be to do. The framework that we implemented before for TNE2, where it was the adjoint weighted Hessians of fluxes and source terms, worked okay, but I think the full linearization works a little bit, or it works significantly better, rather. It's a much more exact error estimate. So
Thank you.
it would require a lot of implementation.
Okay, how about a final question, because I think it'll be straightforward, and then we'll pause for break. So someone asks, is your previous solution interpolated onto the new grid, or are you running it again from scratch?
I interpolate. Yeah, I interpolate both the flow and the adjoint solution onto the new mesh and restart from there. But the adjoint interpolation doesn't really seem to have too significant of an effect on the convergence. So maybe I don't even need to do that.
Okay, great. Why don't we pause there then? Thanks again, Brian, for a great talk. We appreciate it. And we'll pause now until 8:25 Pacific time. So in about 7 minutes, we'll come back right at that time. Okay. Okay, welcome back. We are excited to have a nice session of lightning talks and another featured talk the rest of the session here. So I want to first introduce our speaker, AASHA, who will be talking to us today about numerical simulations of flow over NACA 0012 airfoils pitching at low frequencies. So AASHA, if you can hear us, and if you'd like to turn on your video, the stage is yours.
Thank you very much for the introduction. Hello everyone, I'm Asha and I will be talking about the work done by undergraduate students in the Department of Mechanical Engineering and BMS College of Engineering, titled Numerical Simulation of Flow over NACA 0012 airfoil pitching at low frequencies. It was done under the guidance of Dr. Ramesh Kollu and Professor Ramesh Chalkapuri. We have sectioned our work for the current presentation as seen on the screen. Actually, we had originally planned on doing experimental validation, but due to the circumstances created by COVID-19 pandemic, we have pushed it as our future work, which I'll be talking in the conclusion part. Thank you. There's a number of situations, especially in maneuvering of aerospace and underwater vehicles, where UAVs and aircrafts, submarines and REVs, etc., where their components oscillate at low frequencies. To mention a few, when an aircraft has to change its direction, it moves its ailerons and rudder at low frequency. Similarly, large marine species like whales use their fins to maneuver and change direction by oscillating them at low frequencies. In all of these cases, the fluid flow can be considered incompressible and quasi-steady. So we aim to study such nature of flow, where the flow is over the oscillatory component. To dynamically limit such a situation of pitching airfoil, pitching motion of a component, we have used one of the simplest symmetric airfoil NACA 0012 by pitching it sinusoidally. This is the equation number 1. Which represents the sinusoidal pitching motion of an airfoil. For our case, the mean angle of attack is 0 degrees, amplitude of oscillation is 9 degrees, and as frequency, as said before, it's very low, which is 0.15707 radians per second. We conducted static simulations for a number of angles of attack. To compare them with the results obtained from quasi-steady flow. To model the fluid flow, we have used flow parameters as shown in the table here. We have used incompressible rank solver available in SU2, which solves the equation given in equation number 2. Here, pressure velocity coupling is realized through Corin's artificial compressibility, and we have picked a constant density model as our density is unaffected by pressure or temperature changes. Again, based on our Reynolds number, we had to do the turbulence modeling, and we have chosen Mentis assisted turbulence model to compute the turbulent component of the viscosity, and dynamic viscosity is same as mentioned earlier. Ours is constant temperature flow analysis. Finite volume method is implemented in SU2 for space integration, and median dual control volumes, as shown in the figure, are formed on primal grid for the same purpose. We have used a flux difference splitting scheme for integration of convective fluxes, and also applied muscle approach to achieve higher order of accuracy. And similarly, for viscous fluxes and the gradients, we have implemented Green-Guts method for our case. For time integration in static analysis case, implicit Euler scheme is selected, and dual time stepping second order matching method is used for dynamic analysis case, where again the unsteady problem is transformed into a steady state problem for each physical time step. The linear solver we picked was HMRS, and we also picked a line rate preconditioner. The figure shows the mesh we use. It's a C-grid, 2D C-grid structured mesh. The specifications are as tabulated here. We use the boundary conditions of no slip wall condition in airfoil and far field boundary condition on the far field. For oscillatory motion, we needed mesh movement, and we picked polymetric deformation procedure in SU2. These are the pictures, captures at 0 and 9 degrees angle of attack obtained by polymetric deformation procedure. Here, the first airfoil moves because we have given that as the boundary surface, and accordingly, the whole volume of the mesh deforms to accommodate the changes. We did grid and time independent study. For grid independent study, we picked 3 progressively fine grids, and based on the results, we picked mesh number 2 with 256 points on the airfoil. Similarly, for 3 different time steps, we conducted time independent study over the course of half cycle, and based on the results obtained, we used 0.11 second as the time step for our current case. To compare the results obtained, we used another open source CFD platform, OpenFlow, and the conditions were made same as much as possible. For static analysis case, we used PisoFlow, which is an incompressible flow solver. And for dynamic analysis case, we used Prempel algorithm with displacement Laplacian mesh morphing methodology. Coming to the results, we have sectioned the results as velocity contours, pressure contours, streamlines, and flow coefficients. As you can see, the velocity contours in static analysis case, there is no pressure region on the upper surface and high pressure region on the lower surface of an airfoil for negative angle of attack, which gives a negative lift due to the pressure difference. Similarly, the opposite is seen for positive angles of attack, and the difference in pressure region creates a lift. The pressure contours show the same nature as velocity contours. We have plotted them for the same angles of attack for each section. And similarly, the streamlines show the same nature as shown by the previous contours. There's no fluctuation. There's no boundary layer turbulence formed. Coming to the flow coefficient, which is our major concern. Here you can see the nature for both lift and drag coefficient curves are very much as predicted. The CD value increases on either side of CD degree angle of attack with increasing angle of attack as the drag increases with increasing angle of attack. The magnitude of angle of attack, and similarly lift is linear as lift increases with increasing angle of attack. Here there's no stall, there's no static stall seen for the range of angles of attack which we have performed. To verify the mesh and numerical algorithm we used for study, static simulations were conducted based on the specifications given in NASA's Langley Research website for assisted turbulence model, and the results obtained for 10 and 15 degrees angle of attack showed less than 1% of deviation. So we thought we are good to go with the given mesh and numerical algorithm. We have plotted a CP curve along the chord line for selecting our angles of attack, and they are seen very smooth, which again shows the absence of boundary layer turbulence. Coming to the dynamic analysis scales, these are the velocity contours again for the same angles of attack. These are the pressure contours, and these are the streamlines. So as it can be seen from all these contours and streamlines, for the results from both static and dynamic analysis cases are in good agreement with each other, and for SU2 obviously, and for OpenFlow there's a slight difference seen. This is in accordance with the quasi-steady nature of the flow, as I mentioned earlier. The coefficient of drag, if we see on the top bottom left, for static and dynamic case, they almost overlap, which is in accordance with the quasi-static nature of the flow. There were minor fluctuations during the downstroke for SU2, but they subside and form a periodic pattern over the course of time. There were major fluctuations seen for open foam, and also values were quite higher. Similarly, the lift coefficient curve overlap for both static and dynamic analysis case, showing the quasi-steady nature of the flow. Hysteresis were negligible, and there was a smooth periodic pattern over the time. The CP curve again is very smooth, which is plotted against the chord length, which is different for open foam. However, I will be reasoning them in the conclusion slide. We have tabulated a few data for selected angles of attack. The differences, especially in the dynamic case in terms of CD, will be pointed out in the conclusion slide, which is next. So in conclusion, the static and dynamic results are observed to be in good resemblance with each other, which is in accordance with the quasi-steady nature of the flow. Over the course of few cycles, flow and flow parameters developed a steady periodic pattern as seen in the previous slides. The major difference was seen in the values of CD for dynamic case, which is by 0.16, which could be attributed to the different mesh morphing mechanisms used in both the software, and also that could be attributed to the boundary layer turbulence formed. Again, because of which kinetic energy of the fluid also gave rise to waves, and trailing edge vortices were formed and were shut down at 9 degrees angle of attack. So overall, in conclusion, for low frequency quasi-steady conditions, we can agree that static and dynamic cases are found to be similar. Also, we intend to compare and see the results for CM, CF, and boundary layers. Coming to the future work, we intend to run more number of cycles for both the software and find out the differences in association with the respective modeling techniques and solver algorithms. Also, as mentioned earlier, we intend to do the experimental validation part, where actually we are already done with airfoil fabrication and electronic setup of the pitching mechanism. Only the data reading remains, and comparison and validation remains. These are some of the references which we have used for the current study, and thank you very much for your attention. I'm happy to take questions if any.
Okay, thank you, Asha. Yes, we have time for a question or two, so I will read one for you. Someone asks, the lift coefficient results seem quite different between the two codes. What is the experimental result published by NASA for this airfoil, for instance?
Actually, the results from SU2 are quite in agreement with the results published by NASA, where it's around, like, I don't really have the data in my mind for now, but they were very much in agreement, which was about 0.9 for 9 degrees angle of attack, if I'm not wrong, around that value.
Okay. And I had another question from myself. This is just to clarify, this is with the density-based incompressible solver inside of SU2, correct?
Yes, sir.
Okay, great. If anyone else has a question, you can leave it in here. Someone else commented that they do notice some differences between SU2 and open foam in your results. And I'll add, I noticed that it looked like there was maybe some separation or some transients in the open foam results. Could you comment on that a little bit?
Actually, sir, because of the time constraint of this, it was a final year project, and so we had like only not much of time to work on this. So we had this time constraint for this conference, right? So it was only the first cycle, and even the simulations obtained can't be trusted for now. So the separation, first we reasoned it because the mesh morphing mechanism was different in OpenFlow. Also, the mesh refinement was not very good. We are working on it, so we are still working on it to like see which is like how to minimize those fluctuations.
Yeah, it sounds good. I'm curious if maybe with the dynamic mesh motion, that's, you know, those there might be something there. So I actually don't know. Maybe SU2 is missing something in that case. So I have to investigate a little more. So anyway, thank you for a great presentation. So we'll have to transition here, but thanks again. And if there are any other questions for you, yeah, of course, I'll forward them along. Okay, so if anybody else has questions for AASHA, please just leave them in the window. Okay, at this point, I'd like to transition to our next speaker. So we have Connor McMullan talking to us today about aerodynamic innovation through machine optimization. So Connor, if you're there, the stage is yours.
Hey everyone, thanks for tuning in today. I'm Connor, I'm an AI developer. I'm going to be talking to you today about new directions with machine learning in CFD. This is going to be a lightning talk, so I'm going to be talking about ideas in broad strokes. If you are looking for technical details and all the good stuff like stats and numbers, then I'll be uploading a longer video at the end of the conference. Okay, let's begin. Next slide, please. Thank you. So ML in CFD is a very exciting area of research, but the focus of the more innovative work tends to be on the CFD side. We're seeing lots of really exciting stuff with optimization and prediction, but we're not seeing a whole lot of the advanced ML research coming into CFD. So this is where my work comes in. Recently, ML has moved towards generative models where we can teach machines relations about data and ask it to generate data objects. So this is the sort of technology that's powering deepfakes. And this technology has a lot more promise than making Mr. Musk look a little bit funny. It has a lot of potential to ask machines to design things with a very data-driven approach. And it's how we ask machines to design things like airfoils. Okay. There's a little bit of foundational work to get familiar with here. I will go over it briefly in the talk, but I'd strongly recommend that you go home and you research this in your own time. Generative adversarial nets are the deepfake architecture that we'll be talking about. It's very simple. It's two neural networks that compete against each other. You have one neural network that's designing something, and you have one neural network trying to tell if it's real or fake. And because you have these competitive networks working against each other, you can create networks that are highly adept at the task they're trying to achieve. Bezier surfaces, this is a dimensionality reduction technique. We'll talk about this a little bit more when the time is right. And swarm AI management. Now, swarm AI is defined as a machine that can make multiple workers work in synergy and cooperatively instead of individually. I use this with some success to coordinate drone swarms, and in this talk, I'll be using it to talk about aerofoils and how a machine can manage multiple surfaces on an aerofoil. Next slide, please. There we go. Okay, so this is how we manage surfaces within Swarm AI. This is a novel technique. It's very technical. I won't be going over all of it in this talk, but it is electric fluid analysis. And this is how we decide what behaviors are good in a swarm and what behaviors are bad. We see this purple fluid here. It's electrically charged and it's being orbited by an electrically charged particle. So there's an attraction between the two. We relate the orbit speed of this particle to the performance of the network. So if the network is doing very well, then it's a fast speed and there's not much of a spike in this reading. But when the network does poorly, we can see there's a larger spike here on Fig 2, and we can analyze the behaviors that led to that. This allows us to look at surface modification. When a neural network is modifying a surface, we can say, okay, this surface is working out, this one is causing problems, let's remove it before things get worse. One of the most important parts of machine learning is unsupervised learning. This is taking information from our data input and trying to find the key variables, the things that really make it tick, so that we're giving our machine less to work with and we're giving it less noise and fluff. Neural networks work best with fewer input dimensions, and this is why we're using Bezier surfaces instead of complete pointwise meshes. Bezier surfaces, if you think of a puppet controlled by a couple of strings by a puppet master, can create very complex and realistic movement. It's a similar idea with Bezier points. You have a couple of control points that can dictate these very complex surfaces that we can use to design our aerofoils, and we can use to give a machine a little bit more autonomy when it's designing the aerofoils. So instead of telling it to do it our way, we can let it do its way. Now, this is the first novel contribution to this talk. We talk about using the backpropagation algorithm to transform Bezier points in space. So instead of asking a neural network to look at some data and transform it in the way that we want, we say, these are literally the points, the Bezier points that we are feeding. We give it to the network, we run it against SU2, so we have some outputs. It's a drag coefficient, a downforce coefficient, for example, and then we backpropagate that through the network. So we can identify the points that are causing the most error, the most drag, the least downforce, so on and so forth. This is commonly applied for other tasks like image recognition, but it's about taking the abstract idea that underlines machine learning and applying it in a slightly different way to suit CFD. This is the next part. This is autoencoders. We talk about the idea of teaching machines to do smart data compression. And this is important. As I'll go into the next slide, it all relates back. But this is important to teach a machine what are the key points, what really matters, what's fluff, and what do we actually have to focus on to build better aerodynamic surfaces. When we encode and decode data, when we compress it down and stretch it back up, we create something called a latent space. This is a space that machines understand very well. Human beings don't really understand at all. It's the machine's abstraction of the data that it is processing. And when we look into this latent space, we can sample from it to create new shapes, new aerofoils. So for example, if we learn how to encode and decode an entire front wing of a car, a plane, whatever it happens to be, we can move around this space and start experimenting with new ideas, with new generations and new designs that we hadn't thought of as human beings, but the machine can infer from data and information. Next slide, please. Thank you. So we can train an autoencoder to recognize certain types of wings. In this particular example, I've used a mock Formula One front wing, and I've trained it to encode and decode types of this wing and modifications of this wing, permutations, to create a rich latent space where the machine has a good understanding of what's important in a front wing, what are the key variables, what points matter more than others, and what's a bit more generic, like the wing end plates, they pretty much don't change, but the surfaces in between, the heights, the rides, the curves, all that sort of stuff. It's not enough to create a latent space, however. We need to think about how do we direct a machine towards doing something with this latent space? How do we teach it to infer some new information, some new designs from this? So we go back to the previous idea where we talked about the movement of points and adjusting points and trying to make better surfaces and better aerofoils from the ones that we started out with. And we use this to create a richer latent space. And we can encode various data here, and we encode it down into latent space, and we assign it the error function. So if we have a wing that's very badly performing, we give it a big error function, and we say, right, this has a big divergence, stay away from this point, pushing our network away from this. If we have a wing that's doing quite well, we don't push it away from this point that much because it has a good performance. And by naturally following the divergence of these points, we can get to an optimum value locally at the very least. This is the technical implementation. So I said I wouldn't be too heavy on the technical details here. I'll try not to be. The optimization function given for this network were the drag and downforce coefficients. In fact, it's the drag coefficient plus 1 over the downforce all squared. And this places emphasis on both factors equally. It says if you can get a low drag design, that's great. If you can get a high downforce design, that's also great. I had to implement the logistic regression myself, so I couldn't use any pre-built frameworks like TensorFlow or PyTorch because it was a bit of an exotic idea. That's the way it goes. Mesh smoothing, I used an algorithm provided by MIT to remove anomalous points that were floating about and things that the network hadn't got quite right during the training phase. I used SU2 as very simply a simulator. It would compute the required coefficients that I'd need to feed back into the network, and I ran it on a Tesla K80 GPU. It's quite a powerful piece of hardware, but it's nothing too crazy. Now, what I'd like to talk about here is one of the more interesting results of the network. This is not everything. This is something that's simply interesting to point out, and one of the best ways to describe and understand why this is important and why we should have machines working on these types of problems instead of just human beings. So I will attract your attention towards the end plate here. This was generated completely by the machine and smoothed over a bit by the smoothing algorithm. there are 4 holes in the end plate placed right at the intersection of aerofoils with the end plate. So these holes, they're not quite as clear as they are, well, not quite as clear as they seem in this diagram. Here we can see there is an open inflow vent, and this allows air to flow in, and then we have an outflow vent, and that allows air to flow out. So when I first looked at this, I'm not an aerodynamicist, I had no idea what it was doing. It becomes a lot more interesting when we run it with some simulations, and this was really cool. What the machine had decided was that the tires of the Formula 1 car were the biggest source of drag. There's a lot of drag, there's no downforce, they don't serve a whole lot of purpose, but it couldn't get rid of them because it wasn't optimizing the tires, it was optimizing the wing. So what it did is it put these holes in the end plate here so that there would be a pressure sink created and it would deflect air away from the tires. When you have the wings here on the Formula 1 front wing, it's very simple aerofoil, you have high pressure on the top, low pressure on the bottom, and the placement of the holes by the network would pull this high pressure air out and away from the wheel, and also would allow the channels here that are further away from the end plate to go undisturbed and into the floor diffuser here. Now you can really see my technical skills shining through here. This is a heat map of drag against the tire before and after the wing modification. Here it's a very general gradient, there's not a whole lot going on, it's not that interesting, it's just hitting the tire and it's creating drag. Here you can see that the holes in the end plate have deflected air to a very high pressure point here, but overall have reduced the amount of drag that's on the tire. So to finish this up, I thought it was important to talk about why SU2 works for AI and CFD. You couldn't run this on other software. It's something that's very well suited to SU2 because SU2 is a research and academic driven simulation lab. It's not dictated by large companies. It doesn't have margins to meet. It doesn't have project requirements that you find in enterprise. It's open source. It's available to the community. And it's a really interesting example of innovative work when you release something to the community. I believe Tom also talked about earlier at the start of the conference, the idea of having a city. And you can build all this shiny new research, but you know that the underlying fundamentals, the underlying core parts of the code are going to work and going to work well. And that's why SU2 works well for this sort of scenario, because you're doing a lot of exotic research, but you need the fundamentals to work. Okay, a bit of a short talk. Thank you very much for listening, and I'm happy to take any questions.
Great, Connor. Thanks for that. Very interesting new work. I think this and the next talk are both going to show some things that are a little bit different and new for our community. So I appreciate that very much. Okay, we have plenty of time for a few questions. So a few are coming in. I'll read one or two out to you. So someone asks about the computational expense. So how expensive is it to involve machine learning into this optimization problem on this kind of airfoil?
It's expensive enough to not run it within SU2. So the training time of the network was about 6 hours, and that was coming from a couple of blocks that were just sitting as OBJ meshes. I had to use SU2 as a separate module, so I had to hand off computation to SU2 and run it there. I couldn't run it within SU2. In terms of computational cost, you definitely couldn't run this on your laptop. You do need some serious GPU hardware. But that's just the nature of machine learning, and that's one of the problems with machine learning, that you do need some pretty hardcore hardware.
Yes. Someone else asks, did you consider the front wing and the whole car in the back for your CFD simulation? Or maybe you could just reiterate which parts you were including in the CFD simulation.
Sure. So that's one of the cool things about this approach. It considers the entire car. So there's a stitching algorithm that just reinserts the wing onto a certain point on the whole car, and then the whole car is run through the SU2 simulation. So it's trying to work with a lot of factors, not just the tires, but there's also a ground effect diffuser that's trying to work with. There's a rear spoiler, there's air vents, there's a whole complicated mess of stuff that is trying to optimize and work around. And that's quite cool because it allows you to design a front wing that works in synergy with the car and doesn't do something gimmicky. That's just cool for one thing, but not much use to anything else.
Yeah, so I'm wondering, I think a couple other folks have asked, what was the size of the grid then in these calculations if it was the full car?
In terms of Is there another way you could ask that question? I apologize.
Just, when you were launching SU2 in the background, when you were actually running the code to, you prepare a config file and also a mesh file. I'm just wondering how, what was the size of that file in terms of either number of cells or even just like raw size in gigabytes, if you know off the top of your head?
I know the gigabyte size. The raw cells I put in my paper, so I can get that for you. But it started off at 26 megabytes, and then by the end of it, it was looking at 784 megabytes.
Oh, wow. Okay. So it increased quite a bit.
Oh yeah, it did.
Okay. There are a couple more questions that I think we'll forward to you. We're out of time here. We have to transition, but Connor, thank you again for the talk. I'll pass along the questions to you here, maybe through the interface or offline. Okay.
Perfect. Thank you very much.
Okay. So our next speaker is Philip, who is going to be talking to us about another AI work is combining SU2 and graph neural networks for fluid flow prediction. So Philip, if you're there, take it away.
Okay, am I unmuted?
Yeah, sounds good. Go ahead.
Cool. Yeah. Okay. Let me see. Can I control the slides? Yeah, it seems so. Okay, nice. Yeah, originally, for some reason, when I prepared this presentation, I thought it would be a 15-minute one, so I might go a little bit over time, but not too much, I think. In any case, yeah, I'm Philip. I'm going to present combining SU2 and graph neural networks for fluid flow prediction. This is joint work with Tom Economon, which everyone knows, of course, and my advisor at CMU, Zico Coulter. And this work was done while I was interning at Bosch last summer. Next slide. Is it going? Okay. Over the past decade, deep learning has been successful in solving diverse tasks, especially in the visual domains, with a few examples in object detection and classification presented here. And of course, everyone here knows that performing CFD simulations can quickly become very complex and computationally expensive. And so recently there has been a lot of interest in exploring the usage of machine learning methods in order to predict fluid flows in a more efficient manner. Many of these recent works employ standard convolutional networks to this problem. And these are basically just the default type of model used when dealing with structured data, such as images for visual tasks. But this approach comes with some drawbacks. Since these methods employ standard convolutional networks, they are not directly applicable to traditional CFD problems, which are often formulated using unstructured meshes. So this requires the problem to be converted into images with predictions that are also made as images instead of the natural CFD meshes. Another issue that comes up, as we will see in our experiments here, is that these convolutional models tend to generalize poorly once they move outside the range of physical behavior they were trained on. Here we see an example of a recent paper in which the training and test distribution of parameters in red and blue, respectively, are very similar. These convolutional networks are very good at interpolating the training points they have seen before, but usually not that good at extrapolating to conditions that move far away from those they have seen previously. In order to address these issues in this work, we develop an architecture that combines both graph networks and a CFD simulator, which is SU2 in this case. The graph neural networks are a type of machine learning model that has increased in popularity recently due to its ability to process more general and structured data represented as graphs. And the usage of graph networks here enables our method to work directly on non-uniform meshes, allowing the flexibility to accept CFD problems in their native formulation. And we also embed a differentiable CFD solver into the model, which allows it to take advantage of traditional fluid simulations, enabling better generalization while still allowing the model to be trained end-to-end, which means that all components are trained at the same time by differentiating all the parameters with respect to our objective. But for us to be able to use SU2 in a deep learning model, it needs to be able to interact with the deep learning components, in this case represented by PyTorch, which is the framework we use. And to this end, we developed a PyTorch interface that allows SU2 to be used as a regular deep learning module inside a larger model. This capability is exposed through a reasonably simple interface. The CFD simulations are defined using SU2's native configuration files with added fields that define which components of the simulation will be differentiable and exposed to PyTorch. In this case, we are outputting the flow fields of the simulation and performing differentiation with respect to the positions of the input mesh, as you can see on the left. And after this is defined, using SU2 with PyTorch is very simple. You just define a module and use it as if it were a normal PyTorch module. And then the framework handles the forward pass and the differentiation and everything else. So having defined the basic components of our model, we can take a look at the tasks we're going to be exploring first. Our goal was to simply predict the fluid flow around an airfoil given the simulation mesh. We used a NACA 1212 airfoil and performed steady state simulations of the inviscid flow around the airfoil as our ground truth target. And we aim to predict the X and Y components of the velocity and the pressure fields. So in this presentation, we're going to be only looking at the X components just for simplicity. So in order to vary the physical behavior of our simulation, we sample pairs of physical parameters with the angle of attack ranging from -10 to 10 and the Mach number ranging from 0.2 to 0.8. And we can see in the figures here that these parameters generate very qualitatively diverse physical behavior, from smooth flows as in the left to shocks as in the right. And so, well, having defined our task, let us look at the full model now that we will be using. We call the model the CFD GCN, as it combines graph convolutions and CFD simulations. And so we're going to take a look at it part by part. So the first thing, as mentioned before, is we take as input the meshes used for the simulation instead of images, and our model takes as input both a fine mesh, the full mesh we wish to use to predict the flow, and also another coarser version of that full mesh. In order to be processed by the model, these two meshes are represented as graphs, where each node contains the position of the mesh node and also its sign distance function from the airfoil. This just helps the network encode better information about the mesh we're dealing with. So the mesh we use the meshes we use, the coarse one is significantly smaller than the fine one. It has 20 times less nodes than the fine one, and it's thus much faster to run simulations on. This is what our model uses to run a CFD simulation and still be efficient. In the figure here, we can see a sample simulation with the same parameters. On the left, we have the coarse mesh, where it's coarse enough that you can actually distinguish the mesh elements, whereas on the right, the fine mesh is, at this resolution at least, it's fine enough that it looks basically smooth. And our model also takes as input the physical parameters of the simulation in order to be able to predict the behavior of the flow, of course. These parameters are appended to the graph as node features and then passed on to be processed by the model. And so one of the main two parts here is the CFD part. So we take in the coarse mesh and the physical parameters and perform a proper CFD simulation in SU2. Since the coarse mesh here is 20 times coarser than the fine one, this can be performed very quickly. And the output of this coarse simulation is then upsampled and appended to the processed graph features, which we will get to in a minute. And then this is further processed to generate the final output, which can be seen on the far right. And so the second main part of our model here is what we call the GCN part, because it uses graph convolutions. GCN stands for graph convolutional network. And so it consists of a sequence of what are called GCN layers, which process the original fine mesh and the physical parameters represented as a graph and generates the output. So I mentioned the GCN layers in the previous slide. A GCN layer is just a function that operates on a graph. One GCN layer processes an input graph X with n nodes, and where each node has a certain number of features, and it outputs a graph with the same structure, but with different features, maybe even a different number of features per node. So the mathematical formulation of the update is presented there in the slide, but at a high level, it's easier to understand at a high level what is happening. which is that the GCN layer takes in the features at each node, aggregate informations from neighboring nodes, taking into account the graph connectivity, such as the degree of each node, and it maps this to a new feature representation per node using a learnable linear transformation. And so when you stack a bunch of these with nonlinear activation functions in between, you can learn very complex functions on graph structure data. So finally, after having defined our model, we can see that by taking the loss on our predictive flows, so comparing the predictive flow to the true flow, taking the loss, and then we can then differentiate that to update the GCN weights by backpropagation, which means just updating the parameters using the derivative of the loss. But on top of that, due to using SU2 and its differentiation capabilities, we can also backpropagate this error through the CFD simulation so that we can also optimize the coarse mesh by changing the position of every node in order to further reduce the loss. Thus the model can be fully trained end-to-end. So this is a model with many moving parts, and as such, we tailored our experiments to ensure the contribution of every part. And so to do that, we analyze a few ablated versions of the full model. So I'll just go over those before looking at the experiments. We have what's called a pure GCN baseline. This baseline consists just of the GCN layers, and this ensures that the coarse simulation is actually helpful to the performance of the model. And on the flip side of that, we also have a baseline which consists just of the CFD simulation, the coarse simulation without the GCN layers. So we just upsample the coarse simulation and use it as the output. And this ensures that the GCN layers are also important to our results. And finally, we also have a baseline in which we do not optimize the coarse mesh as if we were using a CFD simulator that is not differentiable, unlike SU2. So when compared to the pure GCN baseline, we can see that the baseline actually, so actually before I get into that, let me go back here. It actually skipped a slide. Okay, let me go to this one first. Yeah, so for this task, we simply train and test with the parameters that were sampled from the ranges described previously. The train and test sets are separate, but the parameters come from the same parameter distribution range there. And here we can see just a qualitative example of a prediction from the CFD GCN showing that it can actually make good predictions. And then for the slide I was gonna, yeah, it popped up before. This is just the training curves for that task. And we can see that the performance of the pure GCN baseline and the CFD GCN are similar, but the baseline actually outperforms it a little bit. But this is, as we'll see in the next experiment, this is due mostly to overfitting to the distribution seen in training, since the test samples here, though they were not seen before, they come from a similar parameter range, and this can be interpolated from the training examples. And so in order to show this, in our next experiment, we demonstrate the strong generalization abilities of our model by setting up a task that is very similar to the previous one. Here you go. And so in this generalization task, we separate the training and test set such that in the training set, we have examples only with a Mach number smaller than 0.5. And in the test set, we have examples only with a Mach number greater than 0.5. And so besides demonstrating the capability to generalize to quantitatively different range of parameters, this selection, this training test split also generates an important qualitative difference between training and test set, because at larger Mach numbers, in many cases, shocks are present. And so due to this split, these shocks are never seen in training, but are seen in tests. And so they present a strong test of the generalization of ability of our model to unseen behavior. And so as you can see here in these training curves, even though the performance on the training set is still similar overall, as you can see in the dashed lines at the bottom, our model actually outperforms all baselines in the test set, demonstrating its ability to generalize better to the previously unseen conditions, unlike, for example, the pure GCN model. And here we see some examples that demonstrate the reason for this better performance. The prediction of the test set from the GCN baseline showed here demonstrates that it's not able to pick up on the shock behavior it has never seen. it still produces kind of a smooth flow because that's what it's been taught to do. But due to having access to a core simulation, the CFD GCN is able to capture the nature of the shock and make a more accurate prediction, despite never having seen this before in training. And moreover, when compared to a full-fledged CFD simulation, our model is able to make much faster predictions because it only employs GCNs, which can be run fast on a GPU, and a much coarser simulation. And so to conclude everything I've said in summary, we have shown that by combining a coarse SU2 simulation and GCN layers into the CFD GCN model, it is able to work directly on native meshes. It runs faster than a full CFD simulation, and it also generalizes better than a pure deep learning model. That's it. Thank you for listening.
Excellent. Thanks, Philip, for the nice talk. So I think the clincher is really that you can capture shocks when you haven't even trained on them. So I think that's really interesting. We have time for maybe just one question while we transition because we're running a little behind. Somebody asked a little bit about computational cost. So they want to know, how many times do you actually evoke SU2 when you're doing the trainings in these runs?
Yes. So okay. So how many times? Yes. So when you're training and tests. So okay. So first, of course, to generate the data, you run the full simulations to generate your training set and stuff like that. But besides that, once that is done one time, once you're training or testing, at each run, you're taking your mesh and your physical parameters and you're running one course SU2 simulation per training or test example. And then on top of that, when you're training, you're also running one adjoint simulation to get the derivatives backward. Yeah, so that's basically how it's done. But since it's common in machine learning to train in what's called batches, we train on batches of like 16 or 32 examples per time. We actually run, for example, 16 or 32 core simulations in parallel with SU2. So it actually runs, depending on how many cores you have, you can run it basically at the same time you would run a single simulation per batch.
Oh, great. Thanks for answering and thanks for participating, Philip. Really appreciate it. So now we'll transition to the next speaker. So we have Ettore joining us, and he'll be speaking about implementation and validation of a new actuator disk model in SU2. So go ahead when you're ready.
Yeah, thank you for the introduction. Good morning, everybody. I am Ettore Saetta. I'm very grateful to the SU2 Foundation for giving me the possibility to present our work titled Implementation and Validation of a New Actuator Disk Model in SU2. The authors are Lorenzo Russo, Benedetto Mele, Renato Tognaccini, and me, and this is the result of my master's degree thesis at the University of Naples, Federico II. Okay, so the objective is the introduction of a new general actuator disk model in the release 6.2.0 of SU2, and this study is a part of a collaboration with the Italian Aerospace Research Center, CIRA, within the European Union funded Iron Research Program. So the flow induced by rotary wings is of fundamental importance in many sectors, such as aeronautical, helicopters, and renewable energies. In particular, it is a crucial topic in aeronautics for the airframe integration. So the adoption of an actuator disk model is the most simple and effective method to simulate the effects of rotary wings because of a low computational cost, and it will capture the effects on airframe. However, it neglects the blade geometry and the unsteady effects. So all over the world, many research programs are investigating the distributed electric propulsion, DEP. So the future of propulsion system is moving also in this direction, and so a good actuator disk model is getting a fundamental importance for performance prediction by fast CFD analysis. Also, the Industrial Engineering Department of the University of Naples, Federico II, is collaborating with the CIRA at the DEP research. Okay, the first actuator disk model was developed by Rankin and Flood in the 19th century, while the first CFD application was in the late 80s. And in a CFD code, an actuator disk can be modeled as a boundary condition or introducing a source term distribution in the Navier-Stokes equations. Nowadays, almost every CFD software has an actuator disk model, and here some examples are reported. And also SU2 has a simple actuator disk model that considers a constant pressure jump, and it neglects the swirl term. This is why we felt the need to introduce a more powerful model in SU2. So in an actuator disk model, the propeller is considered as a discontinuity surface through which there are a static pressure jump and a tangential velocity jump, and moreover, it induces an axial velocity respecting the continuity equation.
Ettore, if you're having any trouble with slides, you can just say next, and we can page them for you.
Okay. No, I couldn't listen. Microphone was switched off. So considering the simple momentum theory, we have got a constant static pressure jump across the disk, and this is the case of the actuator disk model currently implemented in SU2. While considering the general momentum theory, we have got a variable distribution of static pressure jump and the tangential velocity across the disk. As I said, the actuator disk model currently implemented in SU2 is based on the simple momentum theory. So it considers a constant pressure jump. It neglects the swirl term, but it also requires a static temperature jump that is difficult to determine a priori. The new actuator disk model, so that we have implemented in SU2, is based on the general momentum theory. So it considers a variable distribution along the disk of the static pressure jump and of the tangential velocity. So because of the fact that the typical available data for the propeller are the thrust and power distributions, the user input is given in terms of thrust, power, and radial force coefficients distributions. On the right, we can see an example of the input file for this new actuator disk model, and we can see that the propeller data are given using an external text file. So without going into details, here the relations that are used to obtain the local force per unit area from the input, the coefficients in input are reported. In particular, the thrust, power, and radial force coefficients are defined using the Renard relations. In order to implement this new model, we face with the problem of the consistency and stability of the boundary conditions at an interface. So for multidimensional problem, there exists theorems that provide only necessary conditions for the stability of the boundary condition. So the guideline is to be consistent with the monodimensional characteristic theory that states that on the interface, we have to extrapolate 2 data from state 1 and 1 data from state 2. Similarly, for 3-dimensional problems, we have to extrapolate 4 data from state 1 and 1 data from state 2. As regards the local mathematical model for this new actuator disk model, the state 1 that represents an outlet for the domain, the static pressure is imposed while the entropy, the acoustic Riemann invariant, and the tangential velocity are extrapolated. The state 2 that represents an inlet, the static pressure jump, the continuity equation, and the momentum jump in tangential direction are imposed, while the acoustic Riemann invariant is extrapolated. After the implementation, we have validated this model using some test cases provided by Chira. Here, for brevity, only an actuator disk with a semi-infinite spinner is shown in this presentation. Here we can see the given input, in particular in figures is shown the input in terms of thrust and power coefficients distribution. The mesh is composed by almost 800,000 of cells with almost 4,000 of elements on the disk. And here the convergence history for some residuals is reported, showing a good behavior of the convergence for this case. Here the value of the CFL is low, but we also did some simulation for more complex geometries with a higher value of the CFL without any problem. So we compared the results obtained with that obtained by the CIRA with using their runs solver named Zen. So here we can see a good agreement between the two software as regard the pressure coefficient contour, the Mach number contour, and the tangential velocity vectors just behind the actuator disk. This is due to the presence of the swirl term, so that before was not possible to obtain. We can find a good agreement with between the two softwares also as regard the distributions of flow properties in axial direction, and we can appreciate also how the momentum theory is respected. Finally, we can find agreement between the two softwares also as regards the distribution of normal velocity and static pressure, the distributions in radial direction at different stations in the wake. So after the validation, this model has been applied to two cases. The first one is a regional turboprop aircraft configuration developed by Leonardo Company within the SCAVIR research program funded by the Italian Ministry of the Research. The grid is composed by 12 million of elements for the alpha configuration. So in this case, the flow is symmetrical. That implies counter-rotating propellers for CPU saving reasons. Here on the left, we can see the pressure coefficient contour at nacelle symmetry plane, while on the right, we can see the pressure coefficient distributions along two wing sections in the wake of the propeller. We can see how there is a variation of the angle of attack due to the presence of the swirl term. The second application consists in a DEP configuration made by CIRA within the Iron research program. And here we can see the cross flow and the pressure coefficient contour at different distances in the wake. We can appreciate how the introduction of the swirl term allows to capture the induced fluid rotation that is opposite to the tip vortex. Finally, I would like to introduce an automatic generation of propeller input. So the problem is that generally, usually during aircraft preliminary design, propeller details are unknown, but we know only overall performance. So in order to overcome this problem, we wrote a C++ code providing the thrust and power coefficients distributions from global data using the implicit theory of optimal propeller. Here, an example of the execution of the code is reported. So giving in input the thrust coefficient, the advance ratio, and the free stream velocity, it provides the variables distributions on the left and the SU2 input file on the right for this new actuator disk model. So in conclusion, we have developed and implemented the new actuator disk model in SU2 with a variable load along the with a variable long and swirl along the radius. Then we validated this model by comparison with the CIRA results, and we successfully applied this model to a regional turboprop aircraft configuration and to a DEP configuration. Finally, we wrote a C++ code to automatically generate the SU2 propeller input based on global data, using the optimal propeller theory. So what's next? We named the version of SU2 with this new actuator disk model. Saetta is the nickname of the Italian Second World War fighter McMullan C200. So if welcome, we are ready to implement this new actuator disk model in the current official release SU2 Blackbird. Thanks for your attention, and if questions, I will be happy to answer.
Okay, thank you, Ettore. And to your final comment there, I think, yes, it would be wonderful if you guys are interested in adding your nice contributions to the main line. So feel free to get involved on GitHub, and we can create a branch and maybe start some discussion there, or open a draft pull request. I think that'd be wonderful. Yeah. So you do have some questions. I think people are pretty interested in your aircraft calculations that you ran. So two things, someone's asked about the size of the meshes for those. And then I would also add, were you running those with the RANS equations, or were those implicit, or what was your set of governing equations?
Okay, for the aircraft, you mean the, I don't know how to go back into the slides. The aircraft.
Maybe we can page it for you. I think the first, the first of the two, the full aircraft configuration. Yeah.
Okay, this one is composed by almost 12 millions of elements. And what was the second question?
Was this in VISID or RANS or how are you modeling?
It's RANS. We use the RANS solver. VISID, the turbulence model, I guess it was the Spalart-Almaraz. Because this activity was developed within my final thesis for master's degree, and actually this simulation was run by the research group of Renato Tognaccini. So I don't know the details of this simulation for this aircraft, but for sure it's runs, yeah.
Okay, great. Yeah, in fact, somebody else has also left a comment that they're interested in the actuator disk model because I think at least one other group has been looking at this, and they are asking if you have a particular branch that you've worked on. So we can take that offline, but maybe I think there's more evidence there that people would like to collaborate with you on this. So yes, we should talk about that further.
Okay.
Okay, so thank you again for a great talk,
Thank you, Tom.
and we'll transition here. So our next speaker coming up is Nitish, who's joining us from TU Delft. And he's going to be talking about Aeroelastic 3D optimization of turbo machines. So they've been working on this capability quite a bit at TU Delft. So why don't you take it away when you're ready, Nitish?
Hey, thanks, Tom. Thanks for the introduction. Hello, guys. I'm Nitish. I'm working as a PhD at Delft University of Technology, and I'm working closely with Matteo and Piero. And I'm going to talk something about the advancements that we have made with respect to the 3D aeroelastic optimization using harmonic balance method. So let's first understand why this is so important, or what is the background behind these kind of methods. Okay, so in the turbomachinery world, there's a lot of novel concepts which are coming along. For example, the BLI engines, which can be used in the blended wing aircraft, or highly loaded turbines, supersonic turbines, which finds application in rocket engines or in organic Rankine cycles. Now, in both of these conditions, in both of these novel concepts, you have a lot of unsteadiness at the inlet. For example, in the modular injection engine, you have annular non-uniformity at the inlet. On the other hand, for the supersonic turbines, you have this very strong shock boundary layer interaction in the stator rotor region, which can have, let's say, severe consequences structurally, but can also have consequences on the fluid dynamic performance. Unfortunately, there's no established method which can take into account these kind of phenomena and do a design for you automatically. And that is where the adjoint-based methods really shine. And so the idea is from this work is to, let's say, propose a framework which can be utilized to address this problem of elasticity design in these kind of turbo machines. In addition, this is also going to set a foundation for multidisciplinary design optimization for next generation of turbo machines, but it's also going to provide a substantial improvement for the conventional turbo machines, which are saturated in their performance improvements. So, well, there are a couple of aeroelastic issues, let's say, phenomena that let's say generally happen in turbo machines. One is, let's say, for example, flutter. Other is forced response, and I'm going to focus more on forced response. So over here you see. So what is forced response? So forced response is the phenomena in which the blade is vibrating, and the fluid, the unsteadiness from the fluid, adds energy into this vibrating blade, which can increase the amplitude of vibration. Now, with this increase in the vibration, the blade can prematurely fail during operation. So the idea is we have to predict which are these locations or which are these frequencies, and to optimize at these operational points so that these kind of phenomena do not occur. And to identify this, what we have to do is to get a Campbell diagram and identify this frequency. So what you see on the center is this Campbell diagram. On the x-axis, you have the rotational speed, which corresponds to the blade passing frequency. And on the y-axis, you have the frequency of the modes. And wherever you have this overlap, so which is indicated here with this red diamond, is the locations where you have the overlap between these frequencies. So when this necessary condition is met, so when your vibrational frequency is equal to the blade passing frequency, that is the location where you can have a forced response phenomena. Now, obviously, this blade movement looks very simple, but they can get very complicated very soon when the blade modes get matched with the disk modes. And these can be very difficult to simulate, for example, in SU2, which currently has only pitching and plunging kind of mesh motion implementation. So what is our goal? Our goal is to propose a framework which is quick, let's say cost efficient, and which can do a design for these kind of design problems. In short, we have to reside into reduced order methods like harmonic balance. Application-wise, we want this to be very general so that it can be implemented for designing propellers or for axial compressors, but also high-speed, small-scale, high-speed turbo machines. So the current framework that, let's say the analysis framework that is currently being used for these kind of analysis is called as a modal superposition method. And it can be divided into 3 phases. So the identification phase, the computation phase, and the structural integrity phase. In the identification phase, you identify the frequencies at which there can be this kind of crossings. In the computation phase, you do the aerodynamic computation, that is the aero forcing computation and the air damping computation, which gives you some parameter about the amount of about the kind of forces or the frequencies you are dealing with. And finally, you use this information to construct your equation of motion based on which you can find your static and your alternating stresses, which can ultimately lead you to the life estimate of the turbine. Obviously, like substantiating this entire framework, this chain requires a lot of manual labor, and let's say one design step can take, or one analysis can take up to 1 week. And obviously, this is something that cannot be synthesized as a design chain because of these practical issues. So the alternative to this method is an energy-based method, which kind of balances the energy between the energy being added by the fluid to the structure and the amount of energy that is being dissipated by the vibrating blade. So it kind of focuses on just 3 parts, which is the point number 3, 4, and 5. But we have to exclude 1 and 2 and the step 6. So by removing the step 1 and 2, we are assuming that when we are doing the optimization, when we are doing the shape optimization, the frequency of the blade does not change. The natural frequency does not change if we change the shape of the blade. On the other hand, by removing 6, okay, we are just removing 1 analysis step, but that is something that can be included, which can act as a constraint for our life estimation. Now, 3, 4, and 5 would be part of our design chain, and then we'll go into that in detail. So for us, since we need to get an optimization, what we want is we're going to use energy method, which I mentioned, and we have developed this within the SU2 code. As I mentioned, we have to reside into reduced order methods, for example, harmonic balance. And now you can see like why forced response is so attractive for harmonic balance method, because forced response can happen at a particular frequency, which we know in advance. And this information can be exploited to run quick unsteady runs computation using harmonic balance. So one primal computation requires 2 unsteady runs, that is the aero forcing computation and the air damping computation. And this also needs the adjoint because we are interested in doing a gradient-based optimization. So the adjoint computation cost is approximately 3 times 1 run's computation. And the parameterization. So there has been a lot of talk happened before already about the parameterization. And we also had some problems with the parameterization by using free-form deformation boxes, especially with respect to imposing geometrical constraints. So for years now, we have been developing this CAD-based parameterization method within our group, and we are proud to, let's say, make it available open access now over GitHub, which is just a parameterization code which uses CAD-based parameters to generate the geometries. It has an inbuilt NURBS class, which can again be utilized to parameterize other geometries, like example duct or pipe flows kind of things. Along with the parablade, you also have an OptiBlade, which is a small code which kind of orchestrates the entire shape optimization framework, which is being done by shapeoptimization.py code inside SU2, and which also has the integration with the code from AASHA, which is the Pygamo package, which has a lot of optimization algorithms, and also SNOPT, which is the optimization algorithm from Stanford. So this is the design chain, or the Aeroelastic design chain that was synthesized from this work. So we have alpha on the left-hand side, which is the set of design variables, and J on the right-hand side, which is the objective function, in this case, the forced response. I'm showing here the parameterization, how it is being done. So alpha consists a set of thickness distributions defined along the camber line. And this camber line can be, let's say, replicated at different Z directions or across the span of the blade. And I'm just showing an example geometry generated by this CAD-based parameterizer. For the volume deformation, you're using the standard methods available within SU2, so nothing fancy there. On the other hand, for the grid movement, as I showed that the movement can become very complicated pretty soon. So I have implemented some new methods which accepts external files to do the mesh deformation. Now with this, I can simulate complicated modal, let's say, vibrational modes within SU2 by using vibrations, by using this external code, external file. For the flow solver, I'm using the solver developed by Antonio Rubinho in the past, which is a previous PhD in our group. Now the code has been extended to deforming grids, which can simulate the vibratory motion within for these kind of turbomachinery blades. A bit of adjoint equations. I'm not going to go into detail, but it's just for the presentation. So if anyone has any question, they can get back to me or find the details in the paper cited in the bottom. Perfect. So what is the status? So we have this code ready, this entire framework working for 2D and 3D cases for multi-frequency harmonic balance problems as well. Additionally, with the help of the parablade, we can now simulate multiple rows of blades simultaneously with mixing plane or harmonic balance. The branch that I'm currently using is actually a fork of Antonio, which is called as Feature 3D Turbo Aeroelasticity. And the link to the Parablade GitHub page is also available here. Some results. So over here, you see a classical Aeroelastic test case performed, or let's say optimization performed on standard configuration 10, which is a very commonly known Aeroelastic test case. Now, as I mentioned, you need two unsteady simulations. So you see the aero forcing computation, in which you have the blade, which is, which is not vibrating. It is constant, but it is under the influence of an unsteady flow, unsteady inlet. On the right-hand side, you have the aero damping computation, in which the blade is vibrating, but the inlet conditions are completely uniform. And from this two computation, you get the work done per cycle of vibration from aero forcing and aero damping, and based on which you can compute the forced response, which is given as JFR. By performing the optimization, we were able to obtain as much as 60% improvement in the forced response computation. Obviously, this is an academic 2D test case, so the improvements are much higher, but I don't expect the same in the real 3D cases. Talking about 3D test case, there is one which is running as we speak. So it is a very well-known another Aeroelastic test case, which is called as the NASA Rotor 67. And what you see here is the blade, which is vibrating. Obviously, the amplitudes are very small, so it's not, let's say, visible to our naked eyes. But you can see the motion in the shock wave because of these small motion in the blade, because of the small vibration in the blades. Now, these shock waves can induce some vibration and can lead to premature failure of the blade. So this is currently running. The computational cost is approximately 36 hours for one design step in 20 cores and can consume RAMs up to 200 GB. The results will be available soon, and when they will be available, it will be communicated through a publication. Future perspectives. So I think one of the biggest drawbacks that we have seen with more and more challenging new 3D test cases is the shock waves are getting very difficult to be resolved in the internal flow cases. And then I think there's an urgency to merge all the turbomachinery features with the develop so that we can inherit all the latest developments with respect to the code, let's say the robustness of the code. The 3D FSI problem, it is in progress. Whenever it's completed, it will be communicated. The CAD-based parameterization is ready for multi-zone problems, harmonic balance and mixing plane. And we are trying to do some test cases with that and see how the performance is. And finally, we want to do more test cases, more validations with experiments, and have as many optimizations as possible in the coming years. With that, I would like to thank you for your attention. And if you have questions, feel free to shoot at me now, or you can shoot me an email at my email address. Thank you.
Okay, thanks, Nitish, for your great talk. You touch on a lot of topics that are being discussed in this meeting, so it's great to see all your guys' progress. There is one question that's a tough one that I want to bring up, even though we're a little short on time. So somebody asks, the aeroelastic vibration frequencies depend on the fluid. So do you need to finally run a coupled FSI simulation at the end to check that your assumed frequencies are okay?
Exactly, yeah. So that would be a good way to test this method. So as I said, energy-based method is a reduced order method. And obviously we want to perform some experimental validation, or let's say to validate the baseline and the optimized design with this modal superposition method, which is, let's say, the more elaborate version of this analysis, and then verify if we are actually getting some realistic improvement by using this reduced order method.
Great, and then maybe one more quick one, because I think you'll be able to take care of it straight away. Somebody asks if the harmonic balance solver is available to the public and what the status is for that.
So the harmonic balance solver is available in there's a particular branch in SU2, which I do not know out of my head, but it is available there. But we have another version which is in the fork of one of the fellow PhDs. But the one that we have internally that works for 3D and for multi-zone problems as well. But let's say there is a lot of push now that we want to merge all of these features as soon as possible with the develop. So I hope there would be some news on that pretty soon.
Okay, great. Yeah, I would say it seems that people are quite interested in all of your guys' nice contributions. So I'll forward you a few more questions here. I think we'll have to transition, but I'll post them your way or send them after the fact. Okay.
Sure.
So thanks so much again.
No worries. Bye.
Okay, and then we'll now move to our final talk. Last but not least, we have Jayant joining us from Stanford, who's going to talk about a very interesting effort that the SU2 team participated in supporting the worldwide ventilation effort. So go ahead when you're ready, Jayant. We see you and hear you.
Can you hear me?
We don't hear you yet. Yeah, there you are. Perfect.
Yeah. Good morning, good afternoon, good evening, depending on where you are in the world. I'm here to close out this conference with a presentation on our community's role in the worldwide ventilator project. This is a project that was started by the folks at Fresh Consulting. Fresh Consulting is a software, hardware, and robotics innovation company based out of Bellevue, Washington. And with this project, what they want to do is redesign and create a new design for a ventilator that can be mass produced for cheap, that can be used in hospitals around the world, where especially ones that cannot afford full medical ventilator units. And this presentation is going to be about the collaboration between their team and ours. So we've been in the middle of a global pandemic that has affected everyone around the world. It has resulted in devastating loss of life and complete disruption to the way we operate and behave as a society. It's been difficult, and I hope everyone has been able to cope with this pandemic in their own way. For me, it was useful to look at silver linings. This conference has been made virtual because of this pandemic, but what this means is my parents who are sitting in India can see me present for the first time, so I'm on that. But yeah, it has been difficult, and in times of this hardship, I was often asking myself, is there something that we can do to help? And an opportunity presented itself when Professor Alonso sent out an email about 2 months ago asking for volunteers to provide computational support to the Worldwide Ventilator project. And a whole lot of my colleagues and I jumped at the opportunity. And within 2 hours of this hastily worded email, we had responses from over 20 people across multiple institutions and from at least 7 different countries. And this is a global effort, and I am the one presenting, but I'm going to try and highlight all the different contributions from different people along the way during this presentation. So the project started with a crash course in medical ventilation. Now, ventilators are these incredibly complex machines that help patients breathe when they can't do it on their own. And this can arise due to a multitude of complications. But in the case of COVID-19, the disease can damage and fatigue the lungs such that the patient is unable to breathe in and breathe out on their own. The ventilator simulates the breathing by forcing air into and out of the lungs, thereby providing fresh oxygenation to the bloodstream. These are incredibly complex machines that can cost up to $50,000 a unit. And they have a lot of electronics on board that actually allow the healthcare worker to fine-tune the ventilation properties specific to the patient in question. And some of the things, for example, that you could control is the respiratory rate, which is sort of the breaths per minute that the patient is taking, or tidal volume, which is the amount of air that is given to the patient each inhale. And there are a lot of electronics enable this customization, but it also makes these units extremely expensive. And while some countries and hospitals might be able to afford an array of these units, for a large section of the world, operating and running a lot of these units is unaffordable. So the question that we wanted to solve with this project was, can we create a new design for a ventilator that is mass producible, cheap, and with as few moving parts and electronics as possible? And is it possible, and while we might not be able to give the full range of customization that a full medical ventilator unit is able to provide, can we conserve core functionality such that it can be used productively in a hospital setting? And to do this, the Fresh Consulting folks went back in time a little bit and found this design for an Army emergency respirator that was published way back in 1968. And it's a very simple device that's based on the bistable fluidic oscillator concept. And I have a little animation to show how it sort of works. So you have air supply, fresh air supply coming in from the left into this device. And as the patient inhales, all of that air supply is directed towards the patient and towards the patient's lungs. When the patient exhales, the air supply, along with the exhaust from the patient, is expelled from the device to be filtered by a hospital if need be. And so using this, and this is basically the schematic of how everything happens. So let's dig a little deeper on how the switching of the two modes actually takes place. I have a 2D representation of the device over here. And again, as I mentioned before, the inlet port on the left is where the fresh air comes in from. There are two main channels, the patient channel and the exhaust channel, leading to the patient and the exhaust respectively. And then in the middle here is where all the magic happens, and that's the fluidic jet oscillation area. So you have a plenum that narrows down to speed up the airflow and create a sort of jet in this area. There are two channels above and below that provide a pressure differential that can push the jet of air either towards the patient channel or the exhaust channel. So let's see what happens when the patient is exhaling. So when the patient exhales, there's a high pressure that's created at the patient port. This travels through the pressure feedback channel to the top part of this fluidic jet oscillation area. So as you can see here, this high pressure flows in through the patient feedback tube and pushes the jet towards the bottom wall of the exhaust channel. And here the Coanda effect takes over. The Coanda effect is the tendency of a jet of air to adhere itself to a surface. So the Coanda effect allows the jet to stick to the bottom channel of the exhaust and go directly to the exhaust port and out of the device. As you can imagine, the opposite happens when you inhale. A low pressure is created at the patient port, which again travels through the feedback channel and actually pulls the jet of air towards the top of the patient channel and directs it towards the lungs of the patient itself. And what the Fresh Consulting folks were able to do was actually combine this and package this fluidic jet oscillator into a device that is both mass production friendly and is able to be rapidly prototyped using 3D printing. So for example, a mold could be created from this design, and these devices could be massively produced using industrial plastic injection molding techniques. And you could also print this device in 2 parts, sandwich them together overnight, and have a working device if you have a 3D printer. And over here, you actually see that the inlet port, the patient port, and the exhaust port have interesting sizes, and that's actually designed to meet common hospital interfaces that you might encounter. And along with being able to 3D print them, the folks at Fresh Consulting actually also have an experimental setup. And this is a video that I'll play in a second. You see here the device is attached with the patient port attached to this instrumented artificial lung. And so let me, and you have airflow coming in from the left into the device. So let me play this. And when I play this video, you'll see the lung actually expand and contract as air goes into and out of the lung. And it's important to note that this lung is not actuated at all. It is a completely passive device. And what that means is that the pressure differentials that are actually created just by the air filling up and emptying out from the lung is able to switch the device operation. So the patient actually doesn't need to be actively trying to inhale or exhale. The device will switch just based on the pressures in the lung. And you can see a lot of dials that are moving up and down. So this is very well instrumented and actually lets us get some experimental data that we can use to validate our simulations later on. And you'll see how that happens. On the right here, you have all the plots that represent some of the data that was collected. The gray lines are all multiple cycles of the experiment done, and the colored lines here, blue is the average inhale cycle, and the orange is the average exhale cycle. So when we inhale, you have a pressure buildup in your lungs, and similarly, you have the volume of the lung, volume of air in the lung increasing, and you have a positive flow rate indicating that there's flow going into the lung. When you exhale, on the other hand, your lung pressure decreases, the amount of volume of air in the lung decreases as well, and you have a negative flow rate that indicates that there's air flowing out of the lung. And here is some of the more experimentally minded folks in our community, like Iran Arad, was able to actually give some feedback into what kind of information would be useful for us CFDers to validate the simulation. So this was a little great back and forth conversation with the folks at Fresh Consulting. And so now we see that the people at Fresh Consulting have a lot of this already done. They have the ability to rapidly prototype. They have a design that nominally works, and they have an experimental setup that can characterize the device performance. So we wanted to really define what the SU2 community could provide in this project. And so one of the things that we can do is provide a physics-based background for the device operation, things like the Coanda effect and jet oscillation. Those are things that are in our realm that we can advise upon. Additionally, running simulations actually reveal some of the internal flow dynamics of the device itself, and we can suggest improvements based on what we see with those simulations. We also wanted to characterize the effects of the valve positions on the flow rates. These actually control the operation of the ventilation, the breathing rate and tidal volume and things like that. And this is the main sort of control that the health worker would have using this device. So having all of this, we wanted to start simulating things. So the first thing that we do when we simulate is create a mesh and discretize the domain. We did both 2D and 3D simulations. The 2D was used to do quick turnarounds on simulations and results to really understand what was going on. And the 3D was more sort of a higher fidelity model in this case, where you're doing more expensive simulations, but getting better results. Pointwise was used to generate these meshes, and some degree of mesh automation was used. We generated a couple of grids and of different sizes, and we realized we can get away with fairly coarse meshes in terms of getting reasonable results for this. So we start simple, and we start with the 2D simulation. We start with steady RANS simulations that sort of just validate the fact that SU2 can at least simulate the two different modes of operation between the inhale and the exhale. But these 2D simulations were super useful in really nailing down the boundary conditions that we use for the simulations, and also things like realizing that the throat isn't choked. So that is not really a design constraint, at least in the current operation of the device. But in the 2D, we can't really represent the cross-sectional area differences that is actually seen by the flow when going into 3D. So we started running some 3D simulations, and here there's the results of the inhale case. And I just wanted to point out here, a lot of these simulations were run by Marco Fossati's group at University of Strathclyde and Becky Zhao at Kaiserslautern. And these beautiful animations, these beautiful visuals are also thanks to Marco Fossati and were made in ParaView. So some of the features of note, you can see how there is this huge, large area change, sudden large area change, which creates large recirculation regions. And what that does is actually reduce it limits the amount of residual reduction we can obtain from these simulations. It stalls after 3 orders of magnitude reduction, but to lend some credibility to the results, we make sure that the integrated quantity, such as average mass flow through the patient port, is converged to 6 orders of magnitude using the Cauchy convergence. And similarly, you can see at the bottom here, you have the contour of the momentum. You can see that the jet stream is all pushed towards the patient port, and you can see that in the streamlines as well, and you have this large recirculation region. And so this is a 3D inhale case. So looking at the 3D exhale case, you see a lot of similar features, just that in this case now you have the contours turned towards the exhaust channel, and you have streamlines coming in from the patient port that go out the exhaust. And these are really features that we want to see in the simulation. And with that actually brings us to the end of what we can do with steady simulations. The device operation is inherently unstable because the patient breathing in and breathing out actually changes the boundary condition at the patient interface, which is right here. So we needed a way to actually model these unsteady boundary conditions, and that required a little bit of development in SU2. And this was some of the work was done by Tim Albring at Kaiserslautern and Miles Morelli at Imperial with the introduction of unsteady boundary conditions into SU2. Using some of the work that was done by Tim in the expression language integration, he was actually able to create this way of defining a time varying boundary condition, and also actually being able to switch between inlets and outlets, because as you can see here, the flow rate goes from positive to negative. So we need to be able to switch between modeling an inlet to modeling an outlet in a reasonable way. And all of this was done, it was incredible how quickly we got these little bits of development and these simulations done, because within a couple of weeks, we were able to give useful feedback to the folks at Fresh Consulting. And so with these unsteady boundary conditions, we wanted to jump into running 2D simulations. And we started simple. We just wanted to do a hard switch between the inhale and the exhale modes. And on the top here, you see the pressure readout, and it oscillates between going above atmospheric pressure and below atmospheric pressure. And you can see from the flow visualization as well as the resulting volumetric flow rate that it is able to switch between the two modes fairly easily. And you'll see that there is sort of a difference between the length of inhale and exhale, and that's something that is common when ventilators are used. You have longer exhales than inhales. So the next step is trying to validate this using a pressure boundary condition that is informed by the experimental data that was collected by the folks at Fresh Consulting. And so to do that, we actually moved to the 3D case, and we did these simulations using a sort of model pressure distribution that is based on the experimental data, but broken up into 4 piecewise linear pressure distributions. And as the cycle goes on, you can see how as the pressure increases, it switches from going into the inhale cycle, which is in red over here, to the exhale cycle, and then switches back to the inhale and then back to the exhale. And this is, again, all being done just by enforcing a pressure boundary condition at the patient port right here. And the mode switching, the resulting volumetric flow rates, all just falls out from the unsteady simulations that are performed. These little spikes that you see at the top of these pressure and volumetric flow rates are actually because of the switch between going from an outlet boundary condition to an inlet boundary condition defined by total conditions. And so this is really honestly a mesmerizing video to watch, and I sometimes find myself breathing to the rate of these simulations. But when we dig a little deeper and go comparing to the experimental data, there's a lot to be desired. So when compared to the experimental data here, we have the pressure and the volumetric flow rate with the simulation in blue and the experimental average in orange. The pressure follows well, and we would expect this to happen because that's something that we are enforcing at the patient port. So it should follow. And you can see how there's 4 piecewise linear functions, pressure functions as a function of time. But when we look at the volumetric flow rate, there is not much agreement between the simulation and the experiment. You can see that the flow rate goes from positive to negative for the simulation far quicker than it does for the experimental case. And similarly, it actually switches from the exhale to the inhale, so going from negative volumetric flow rate to positive volumetric flow rate also earlier than what the experimental data would suggest. What this says is that the switching pressures for the inhale and the exhale is actually closer together for the simulation than it is for the experiment. And that indicates a more sort of sensitivity to smaller pressure changes in for the simulation versus the experiment. And this is where we are with in terms of simulations. And it's an ongoing project, so these are the things that we're working on currently. So just to sort of look back into how these designs have progressed. So we started with this original design that was based on the Army respirator. With our initial simulations, what we realized was that the plenum doesn't actually really do much. It just creates this huge recirculation region that's affecting the performance of the device. So we suggested actually removing that plenum and just having a sort of jet that goes directly into the jet oscillation area. And what that did was stabilize the flow response to the pressure changes. And this was seen in the experiments that were done by Fresh Consulting. And another thing that we realized, this was born more out of the experimental work, was that we needed more control on the ventilation properties like respiratory rate and tidal volume, so that this device could be used productively in the hospital setting. So increasing the number of set screws actually helped us improve that aspect of the ventilator as well. And so just some takeaways that we've seen from this project. The first, and this is really cannot stress this enough, the SU2 community can mobilize very quickly. Going from one email to running simulations took almost less than a week, and that was really amazing to see. This was also the first time I saw rapid prototyping and numerical analysis go to head, and it was interesting to see what happened. Now, with numerical analyses in general, when you're doing shape optimization, the advantage is you can run multiple numerical analyses on many different designs and not actually have to build anything to determine performance. But in this case, when you have rapid prototyping combined with a good experimental setup, you can actually iterate on designs very quickly as well, almost quicker than what you can run unsteady numerical analyses for these devices. And so here, the rapid prototyping actually took over some of those design iteration responsibilities that the numerical analysis usually has. And the numerical analysis played a more qualitative role, where, for example, we saw a sort of recirculation region and said that's not good, we should be able to improve that. And we were able to get better performance by just removing a sort of recirculation region that we were seeing. And so it was interesting to see sort of this role reversal in that sense. And as always, when we have new features like unsteady boundary conditions, they need further validation, and we need to really dig into the discrepancy between the computational and experimental data that we see. And with that, I just want to thank again everyone that has been involved with this project. I'm the one presenting, but it has truly been a global effort. And there's two Fresh Consulting folks that are with us as panelists. So if you have any questions to them, you can also write those down and we should be able to answer them. And with that, I just want to thank everyone and welcome any questions.
Great, thanks, Jayant. That's a really nice overview of the project. So thanks for participating and sharing. You do have some questions. So let me read a couple out loud for you. So first, someone's asking about the differences and the added value of 2D versus 3D simulations for this particular application. So maybe you say words about the two.
Yeah, so the 2D simulations had limited, were very useful in nailing things down, like the boundary conditions and just general, some simple flow physics of the simulations here. You can see we were able to nail down boundary conditions and actually see how the flow is at the throat. But these do not represent the sort of cross-sectional area changes that we could see with the 3D model, which is, I think, in the next slide, where you have these massive cross-sectional changes which cause huge recirculation regions. And so so the 3D models were useful in actually getting good flow rate data and pressure information, but the 2D simulations were quicker and so useful in nailing down solver parameters, for example, and that was super nice.
Okay, there are a couple of questions related to the boundary conditions, so I'll just sort of combine them into one. So somebody was asking if the reversible boundary condition is applied to the whole patch and whether you could do a subset. And someone else asked entirely if just a different boundary condition would make more sense at the patient port.
Yeah, so it is actually applied to the whole patch, and currently it switches based on time. What we would want to do is switch it based on the average mass flow rate at the patient port. So as soon as it goes from being positive to negative, switch it from being inlet to outlet, for example. And in terms of another boundary condition, we did some preliminary like research into what could work if you have flow that is going in and out. And we found it simpler to just sort of use the current implementations in SU2, but have it switch between the two. If you have any suggestions on new boundary conditions, by all means, please reach out. There's a Slack channel on the SU2 that's called the Worldwide Ventilator. Please feel free to join that and contribute to this project if you do.
Great. And then there's another one that I know the folks working on this considered. So someone's asking, is it worth trying DDES or wall modeled LES for this case?
Yeah, so I actually created a mesh for the LES, and we never got around to running that. Those are expensive and it takes a while. We were able to get reasonable results with Unsteady, but as you saw, there are some discrepancies between the simulation and experimental data. So that is definitely something we want to look at.
Okay, wonderful. Well, we're just about out of time here. So Jayant, just want to thank you again for giving this talk and participating. And we'll forward any questions that come along to you, just like we have for the others.
Yep. Thank you. Thank you, everyone.
Okay. And then we just want to do one final wrap up. We just have a couple slides that we'll share with you, and then we can adjourn after that. Okay, so just to send you off on a good note, maybe just a couple logistical things before we end. So first of all, the videos from both Wednesday and Thursday are already linked to the conference page. So you can find those right now if you go. As we've mentioned a couple times, all of the slides from the different presentations are also linked there, available for download PDF. And don't forget that there were other slide sets posted and other videos that haven't been shown during the meeting that are posted on the page as well. So please go check out all the content there. We hope you'll enjoy it. So just as a reminder, we of course want you to get involved in this project as much as possible, and the participation of everyone in the community is what really makes the project tick and makes it a more rich experience for everyone. So first of all, go to our email list or go to the website and sign up for our email list. Anyone who's working on the code, wants to ask about features or develop new things, we can't say it enough, get involved on GitHub, make issues, draft pull requests, just comment, participate in any way you can. It's always better. And if you have any questions for the foundation in terms of program sponsorships, you just want to get connected with other people, we'll try our best to facilitate that. So just contact us either at the email you see there, or I think personally you can email any of us, find us on GitHub. That's also just fine. And so, you know, I don't know about everyone out there, but every time we have one of these conferences, I always end up being very motivated to go and start writing some more code and do more research. I think it's just really great to see everybody's work. I think we can all be very proud as a community of all the great work people are putting in. And I think Jayant's talk is a very nice way to wrap this up and put things in perspective, that, you know, what we do is maybe just a small part of the world, but maybe we can have impact, and we can also help each other and support each other as a community. So with that, I think we'll leave you with just a few words. You know, we hope everyone out there is staying safe, staying healthy. We want you all to be well and stay in touch. And so please go get back to work. We hope to see you next year and see all of the great things you've done during that time. And we hope you'll keep in touch with us. So thank you again, all the speakers, for a wonderful conference, everyone that's helped organize it, the other board members, all the folks out there for joining. So thank you, and we wish you the best. Take care.